Hello and welcome back. In part 1 of this series of videos we saw how a neutron star is the core of a star that remains after the rest of the star has blown itself apart in a supernova explosion. The core has been compressed by gravity into a sphere perhaps 10 or 15 miles across, consisting largely of neutronium, a bizarre element with a density so high that a teaspoonful of neutronium would weigh 4 billion tons. In part 2 we're going to start looking at different types of neutron stars. Not so long ago astronomers thought that classifying them was easy and that they could be placed in just a couple of categories. But like so many astronomical phenomena, the situation is more complex, and it's turned out not to be an easy task to pigeonhole neutron stars after all. As we're finding out, it seems there is more diversity in neutron stars than we used to think. However they behave, all neutron stars have a few things in common. They are all around the same size, with variations in size accounted for by differences in the original mass of the star which gave birth to them, which is known as the progenitor star. They all rotate, but with huge variations between the slowest rotating and the fastest rotating neutron stars yet discovered. The rotation of a neutron star is so constant, so unchanging, that if you were to use it as a timepiece, it would rival or even exceed the accuracy of the best atomic clocks we can build. And lastly, all neutron stars possess a magnetic field, but again with huge variations in the strength of the field. The first type of neutron star we'll look at is known as a pulsar. A pulsar is the name given to a neutron star where particles surrounding the star are accelerated by the intense magnetic field towards the magnetic poles, where they are focused into beams or jets of energy, which shoot out from the poles at about 70% of the speed of light. Note that the magnetic poles are often not aligned with the neutron star's axis of rotation, meaning that the jets describe a cone as they sweep round the sky. In other words, they wobble. If the Earth happens to intercept one of these jets, we see a flash. If it doesn't, we see nothing, meaning that there is almost certainly a huge number of neutron stars we never see. And the only way we can see pulsars is by their flashes. They're far too small, just a few miles across, to see even in the largest telescopes. The vast majority of neutron stars are pulsars, and most of them emit their beams in the form of radio light and are therefore known as radio pulsars, detectable with radio telescopes. However, this is not the whole story. Pulsars can emit visible light, gamma rays and X-rays in the form of jets. It is thought that all pulsars emit these types of radiation when they are young, but over time they lose energy and emit just radio waves. What type of energy we detect from a pulsar is therefore a guide to its age. For example, a typical 10 million year old pulsar will probably just emit radio waves. Let's look at an example. In the year 1054 AD, Chinese astronomers observed what they called a guest star in the heavens. They wrote that it was as bright as Venus and visible in daylight. Accounts vary as to how long this guest star was visible for, but one record states it was visible for a whole year in the sky. Others, however, disagree, citing a much shorter period. The Chinese refer to the object as being below Tianhuan in the sky. We know Tianhuan to be a star in the constellation of Taurus, and we now believe that what they witnessed in 1054 was a supernova explosion. And we also know what is in that same position in the sky today, the Crab Nebula, M1 in Messier's famous catalogue of celestial objects. The Crab Nebula is a supernova remnant some 6,500 light-years away, and it spans 11 light-years. At its heart is a pulsar, one of the first discovered back in the late 60s. Its beams sweep by the Earth 30 times a second, meaning of course that the Crab pulsar rotates at that speed, 30 times a second. But the pulsar is one of a small group which also flashes in optical light as well as at radio wavelengths. Slowed down from its actual rate of 30 flashes per second, here the Crab pulsar betrays itself by flashes of visible light emitted as jets from its magnetic poles. The fact that it emits both radio and optical light indicates a young pulsar, one barely 1,000 years old. But there's more. At the heart of the Crab Nebula there are high-energy particles produced by the pulsar that glow in X-ray light. This time-lapse video taken by NASA's Chandra Orbiting X-ray Observatory shows dynamic rings, wisps and jets of matter and antimatter around the pulsar in the Crab Nebula. The time-lapse was made from 7 still X-ray images taken by Chandra between November 2000 and April 2001. In addition, the presence of high-energy X-ray emissions in the jets shooting out from its poles marks the Crab pulsar as young. In pulsars millions of years old, we see just light at radio wavelengths, an indication that energy levels around the pulsar are less intense and its magnetic field weaker, no longer able to accelerate particles like electrons and positrons to sufficiently high levels to produce X-rays and gamma rays. Notice how the jets of X-rays emitted from the pulsar are corkscrewing around, indicating its magnetic field is not aligned with its axis of rotation. And there's something else. As energy is removed from the system by the lighthouse-like beams, the pulsar's rotation rate slows down. Although over short periods the steady ticks of pulsars are the most accurate clocks in the universe, over long periods the pulsar spins slower and slower. This has actually been measured for some pulsars. Energy is also removed from the system in the form of gravitational waves, but we'll talk about those in another video. This is the Vela pulsar, the first ever discovered. It spins 11 times per second and emits radio-optical gamma and X-ray radiation. The sound you are listening to is its radio emissions, that fast ticking as the Earth intercepts one of the pulsar's jets 11 times per second. Notice again the corkscrewing X-ray jet. There is a class of pulsar known as millisecond pulsars which complete one rotation in less than 10 milliseconds, 1 millisecond being a thousandth of a second. Millisecond pulsars have been detected in radio X-ray and gamma ray light. The current record holder for this incredible rate of rotation is the pulsar PSR J1748, which rotates at an amazing 716 times per second. So the question is, why do these pulsars rotate so quickly? What's the mechanism involved? Well, a millisecond pulsar is the result of a system where the pulsar has a companion star, in other words, a binary system. In this NASA animation of such a binary system, we see a pulsar and its companion, which is a normal star. Both co-orbit around their common centre of gravity. The intense radiation wind from the pulsar strips material from the surface of its companion, which is then pulled onto the neutron star by its intense gravity. As this material falls onto the surface of the neutron star, the laws of conservation of momentum mean that the neutron star will spin faster as a result. The infalling material from the companion is heated up to millions of degrees by the pulsar's intense magnetic field, causing blasts of X-rays that can be seen across the universe. When we see X-rays in the universe, it's always an indicator of extremely high temperatures. This type of pulsar is therefore known as an X-ray binary. But there's a periodicity to this activity. After perhaps a few weeks of intense X-ray emissions, the pulsar's magnetic field reconfigures itself to act like a barrier against the infalling material which is deflected around the pulsar. The X-ray emissions cease and we don't see anything. However, when the amount of material dragged off the companion star builds up to reach a sufficient amount, the magnetic field collapses under its pressure, heats up the material and the X-ray blasts resume. Binary X-ray pulsars are therefore characterized by this on-off X-ray emission. The material continues to fall onto the pulsar, eventually speeding it up to spin once in less than 10 milliseconds. The acceleration of the pulsar's rotation speed does not happen overnight. It occurs gradually over a long period, perhaps as much as 1 billion years. So what is the end of this process? Eventually, the accumulation of material and more significantly the intense wind of radiation from the pulsar, which removes material off the surface of its companion to then be consumed, completely destroys its companion star. The first of these binary X-ray pulsars, which eventually totally consume their companion, was discovered in 1988 and was given the rather fitting name of the Black Widow pulsar. It's located roughly 6,500 light-years from the Earth. It orbits with a brown dwarf or a super-Jupiter companion. The pulsar and its companion rotate around each other every 9.2 hours. In 2010, it was estimated that the neutron star's mass was at least 1.66 solar masses and possibly as high as 2.4, making it a candidate for the most massive neutron star yet discovered. The name Black Widow has since become the descriptive name for all pulsars of this type. Around 24 Black Widow pulsars have so far been discovered in our Milky Way galaxy. This is NISA, an experiment on the International Space Station. NISA stands for Neutron Star Interior Composition Explorer. Its goal is to observe X-rays from neutron stars in unprecedented detail so that astronomers can try and work out their internal composition. By timing with exquisite precision exactly when X-rays arrive as the neutron star rotates, astronomers have been able to create something that would have been unthinkable just a few years ago, a map of the surface of a neutron star. As we have seen, the conventional view of a neutron star is that its intense magnetic field is anchored at two magnetic poles, much like the Earth's, and indeed all the planets in the solar system which possess magnetic fields. Here we see that the magnetic poles are not perfectly aligned with the neutron star's geographical poles, but this is not unusual. The Earth's magnetic poles, for example, lie some distance from the North Pole and the South Pole. What is important here is that the neutron star has a north magnetic pole and a south magnetic pole located near to 0 degrees latitude in the northern and southern hemispheres respectively. This was an assumption based on the way we know magnetic fields behave wherever we have seen them generated from a body like a planet or indeed a star like our Sun. At the point where the magnetic field lines converge on the neutron star's magnetic pole, astronomers expect there to be a so-called hotspot, an area of intense X-ray release. But after a month spent processing NISA's X-ray data from a pulsar called J0030 with a supercomputer — it would have taken a desktop PC a decade to have crunched the data — astronomers finally had the first map of the surface of a neutron star, and they saw something extremely bizarre and completely unexpected. This then is the surface of pulsar J0030. The white markings are the hotspots, areas of intense X-ray release, where the magnetic field lines converge. Like the astronomers, you can immediately see that something is wrong. In the right-hand image there are not 2 but 3 hotspots. The 2 images here represent data acquired at different times, but in both it is clear that if the white spots do indeed represent the pulsar's magnetic poles, all 3 of them are in the southern hemisphere. And why are there 3 in one image but not in the other? In addition, one of the 3 hotspots is an elongated crescent-like feature, hence not really a spot. If it is a magnetic pole, it's unlike anything we've seen or even considered. If all 3 of the hotspots are magnetic poles, that would represent the presence of a magnetic field which is frankly bizarre and complex beyond our understanding at the moment. What does all this mean? Nobody really knows. But recently there has been an intriguing suggestion that we've been looking at things backward. Instead of the hotspots being caused by magnetic field lines converging on the surface, the hotspots are being generated from within the interior of the neutron star, welling up to the surface and then somehow attracting the magnetic field lines to them. If true, the NISA instrument is really living up to its purpose and telling us something important about what's going on inside pulsar J0030. But for now, this map of the surface of a neutron star is truly enigmatic and mysterious. Maps of other neutron stars will be needed in order to understand just what we are seeing. Well, that brings us to the end of this video about pulsars. We've only really scratched the surface here, but I hope you've enjoyed this introduction. Next time, we'll be looking at what is undoubtedly the weirdest type of neutron star, the magnetar. If you thought pulsars were strange, you've not seen anything yet. Please don't forget to like and subscribe. We'd love to keep bringing you more videos like this one, and only by you supporting us can we make that happen. Thank you so much. Don't forget the Space Oddities live programme on Mondays at 8 PM UK time for the latest astronomical news, discussion and chat. Until then, this is Andy of Space Oddities wishing you all the best. Until next time, bye bye. Welcome to the Space Oddities series of astronomy basics videos. In this video we're going to be asking the question, what is a magnetar? A magnetar is the most magnetic object known in nature, a type of neutron star with an extremely powerful magnetic field. The magnetic field of a magnetar can be up to 100 trillion times stronger than the magnetic field of the Earth. A magnetar at the distance of the Moon could pull the keys from your pocket or wipe the magnetic strip on your credit card. If you approached a magnetar to within 600 miles of its surface, its magnetism would, quite literally, dissolve all the atoms in your body, leaving you as just a cloud of electrons and ions. Magnetars have distinct properties which distinguish them from other astronomical objects. They are a type of neutron star, but with a few differences. They're very dense. A magnetar has a mass about 1.4 times that of the Sun, but it's only about 20 kilometers in diameter. They're very hot. The surface temperature of a magnetar can be up to 100 million degrees Celsius, and magnetars are very fast rotating. A magnetar can rotate once every few seconds. However, although magnetars are very similar to a typical neutron star, a magnetar can emit up to 100 times more energy. So how do magnetars form? Up until very recently, it was believed that magnetars are the result of a red giant star ending its life in a supernova explosion, leaving behind its ultra-dense core. In other words, a magnetar is a neutron star, much the same as others, but with the addition of an incredible magnetic field. However, recent research seems to suggest that in fact magnetars may not result from red giants at all, but from another, rare type of star. The most recent research into the origins of magnetars has focused on a new type of star called a massive magnetic helium star. These stars are a few times more massive than the Sun and are rich in helium. They are also thought to have very strong magnetic fields. In a study published in the journal Science in August 2023, astronomers found that a massive magnetic helium star called HD 45166 is likely to become a magnetar. The star is located about 3,000 light years away from the Earth in the constellation of Monoceros. The astronomers studied the star using multiple telescopes, including the European Southern Observatory's Very Large Telescope. They found that the star has a mass of about 3.5 solar masses and a surface temperature of about 20,000 degrees Celsius. Astronomers believe that massive magnetic helium stars must be rare, because to date only around 30 magnetars have been discovered in our galaxy. However, as yet astronomers know little about these strange stars and the process whereby they form magnetars, if indeed that's what they do, which is by no means certain at the moment. Far more research is needed to establish why these stars have such strong magnetic fields in the first place. Magnetars and fast radio bursts. Fast radio bursts, or FRBs for short, are bright bursts of radio waves that come from distant galaxies all over the sky, their distribution seemingly random. They typically last for just a few milliseconds and can carry more energy than the Sun puts out in a year. They are incredibly mysterious and their origin is still unknown. However, there is growing evidence that magnetars may be the source of FRBs. There are several lines of evidence that support the link between magnetars and FRBs. First, the timescales of FRBs and magnetar outbursts are similar. Second, the locations of FRBs are consistent with the locations of magnetars. And third, the energy emitted by FRBs is similar to that emitted by magnetar outbursts. In 2020, astronomers detected a bright radio burst from a magnetar called SGR J1935+2154, which is within our own galaxy, the Milky Way. This burst was very similar to an FRB, and it provided strong evidence that magnetars can indeed be the source of FRBs. However, not all astronomers are convinced that magnetars are the only source of FRBs. Some astronomers believe that FRBs could also be caused by other objects, such as neutron stars with weaker magnetic fields or black holes. More research is needed to definitively determine the origin of FRBs. However, the evidence is mounting that magnetars are a likely culprit. Here are some of the key similarities between magnetars and FRBs. Both are extremely energetic, both are short-lived, both are thought to originate from distant galaxies, both are thought to be caused by magnetic fields. However, there are also some key differences between magnetars and FRBs. Magnetars are known to exist while FRBs are still a mystery. Magnetars are thought to be relatively rare, while FRBs may be more common. Magnetars emit a wide range of frequencies, while FRBs are only seen at radio frequencies. The link between magnetars and FRBs is a hot topic of research in astronomy. As more FRBs are discovered and studied, scientists will be able to better understand these mysterious objects and their origins. Well, that brings us to the end of this brief introduction to magnetars, but just to summarise, magnetars are neutron stars with incredibly strong magnetic fields. Their origins are uncertain, but recent studies link them with a new type of star called a massive magnetic helium star. Magnetars may be the source of fast radio bursts, or FRBs, those enigmatic and powerful bursts of radio waves of incredible power seen all over the sky. Much is still unknown about magnetars, but they seem to be very rare animals in the cosmic zoo. Well, we hope you've enjoyed this video about magnetars. Do keep your eyes open for other videos in the Astronomy Basics series from Space Oddities on our YouTube channel. Until the next time, goodbye.
I plan to tell you about some of the heroes and the stories and their scientific discoveries, and how the stories tend to reveal lesser known works of astronomers that the heroes used to make their famous discoveries. Isaac Newton wrote to his nemesis, Robert Hooke, "If I have seen further, it is by standing on the shoulder of giants," which means if Newton had been able to discover more about the universe than others, then it was because he was working in the light of discoveries made by fellow scientists, either in his own time or earlier. Not was this only a humble brag, but it was also a dig at the fact that Robert Hooke was very short. They really didn't like each other. But it was also an acknowledgement of the people who had come before Newton, whose works he had used to make his famous discoveries. And as we will find, this is the tale throughout the history of discoveries in astronomy. This week I'd just like to summarise what is to come in the next few weeks, and I hope along the way we will all learn something new. From the beginning, mankind looked to the heavens with curiosity and wondered our place in the scheme of things. This makes astronomy one of the oldest sciences. Our curiosity has helped us make great discoveries about the universe and our place in it. Like we are not centre of creation, as first thought, but our planet revolves around the sun. Also that the moon and the planets are other places to explore. Stars are brilliant balls of luminous gas which provide most of the elements we see in the universe today. These same stars have a birth, grow old and die. There are several million of them in our own galaxy alone, and to study them we require instruments and telescopes that can detect energy along the entire magnetic spectrum. We have also found things that baffle us and that stretch our imaginations to the limit. We have only just begun unravelling the mysteries of black holes, dark matter and dark energy, and are now in the position to understand the universe's beginning and how it may end. Every discovery tells a compelling story and has expanded our knowledge of the workings of the cosmos. And, as with most good stories tend to do, our account of these discoveries reveals the heroes behind them. Not the heroes of epic tales or comic books, performing feats of immense strength, bravery, or saving mankind and Earth from annihilation while dressed in tight costumes. Everyday heroes are people who spend their time trying to help others in distress or injured. People who try to improve the environment for everyone. When we think of heroes of astronomy, we tend to think of heroes of classical literature and of science. Generally lone men who persevere against the odds in pursuit of a definite goal. People like Edwin Hubble, Albert Einstein and Carl Sagan. They asked, how did we get here? How does the universe work? And are we alone? These men captivate our imaginations. But the stories of these men and their achievements are far more complex than at first appears. Take Edwin Hubble. Most of us know his name due to the Hubble Space Telescope, but he did not have any part in its conception or building. Hubble is most famous for discovering that our universe is expanding, but he could not have achieved this without his groundbreaking discovery that galaxies existed outside our own galaxy, the Milky Way. Something he could not have done without the pioneering work of a lesser-known hero, Henrietta Swan Leavitt. Also, his work was done using one of the best telescopes built by telescope maker and astronomer George Ellery Hale. Other astronomers, including Vesto Slipher, also observed signs of an expanding universe. Hubble's work also coincided with similar work done by Belgian priest and physicist Georges Lemaitre. So, full credit for the discovery of an expanding universe is hotly debated to this day. Was it Hubble, Slipher or Lemaitre? As for the space telescope that bears Hubble's name, it was originally imagined by Lehman Spitzer and brought about by Nancy Roman and repaired by astronauts in low Earth orbit aboard the Space Shuttle Endeavour, and is still working today. In short, Hubble did make great contributions to astronomy. The telling of his story has evolved to include the amazing feats of a wide variety of other lesser-known heroes. Astronomical discoveries have been made with the advancement of telescopes, the astronomer's invaluable tool. From Galileo, who first turned a telescope to the night sky and recorded what he saw, to George Ellery Hale, who developed new methods to improve and build bigger telescopes, and finally to the giant telescopes we use today. As telescopes got bigger and better, the more discoveries were and are made. Most of the knowledge we know today about the stars and how they work began with the groundbreaking work of a group of women astronomers known as the Harvard Computers. Women employed by the Harvard College Observatory to process and analyze the cutting-edge astronomical data of the era. Women like Annie Jump Cannon, Wilhelmina Fleming and Cecilia Payne-Kapotchkin, who made some of the most foundational discoveries about the stars in the history of astronomy. They developed methods of classifying stars that are still used today. They discovered that stars are mainly composed of hydrogen and helium, and they also broke down barriers for women in astronomy. One Harvard computer, Henrietta Swan Leavitt's discoveries, have ramifications that are still shaping astronomy today. She discovered Cepheid variables, stars whose rate of pulsation is directly correlated to how bright the star appears. May seem a small thing, but Cepheid variables wound up drastically altering our picture of the universe. By measuring these stars' pulsation rates and determining how bright they should be compared to how bright they appeared, Leavitt had given us a new and powerful tool for measuring the distances to faraway objects, and her work directly led to Edwin Hubble's discovery of galaxies beyond our own. Hubble's most indelible contribution to astronomy was a famous and deceptively simple equation describing the expansion of our universe. However, as with many details of our universe, the discovery isn't as simple as it seems. We will learn about the Belgian priest and the astronomer Georges Lemaitre, who had published a similar result several years earlier, as well as other physicists and astronomers who had speculated about an expanding universe based on implication of Einstein's general theory of relativity that were still being explored. Hubble's famous equation is a source of continued debate as teams of astronomers engaged in a century-long mission to determine the exact value of this equation's constant, the so-called Hubble constant, and to work to reconcile different observations into a single answer that can best explain the expansion of the universe. Hubble's legacy also lives on in the space telescope that bears his name. The heroes of the Hubble Space Telescope range from astronomers who dreamed of space telescopes long before humankind even launched its first satellite, to the NASA personnel who tackled daunting scientific and bureaucratic hurdles to make the telescope a reality, to the astronomers who opened and sharpened the telescope's eyes, to the teams of scientists today that have kept the telescope running and making remarkable discoveries for over 30 years. It is also important to remember that astronomy involves much more than the light we can detect with our eyes. What we call visible light occupies just a tiny fraction of the electromagnetic spectrum, and fully understanding the universe requires the ability to detect energy across the entire spectrum to get a complete picture of the cosmos. Hopefully we'll learn how over in the radio regime at wavelengths far too long and energies far too low to be detected with our eyes, physicist Karl Jansky made a groundbreaking discovery in 1932 when he became the first person to detect radio waves from space while working at Bell Labs. A few years later, Grote Reber created the first dedicated radio telescope, an antenna specifically designed to detect radio waves from the sky. Since then, the field of radio astronomy has grown exponentially. We have radio astronomy to thank for one of the most exciting discoveries when in 2019 astronomers synchronized radio telescopes across the entire planet to take the first ever picture of a black hole. Another radio telescope at Bell Labs also made an incredible, if accidental, discovery in 1964. It detected the cosmic microwave background, the faint leftover remnant of the Big Bang, observable as a quiet but persistent hiss in the background of the telescope's data. This radio signal from the birth of the universe led to a Nobel Prize for its discoverers, Arno Penzias and Robert Wilson. Today, several dedicated space telescopes have been launched to study the cosmic microwave background, and teams of scientists are focused on collecting data from the universe's earliest moments in the hopes of explaining how space and time have evolved to what we have today. Decades after Hubble's discoveries of galaxies beyond our own, and just 3 years after the discovery of the cosmic microwave background marked a shift in how we studied the nature of our universe. An astronomer named Vera Rubin uncovered strange inconsistencies in how the stars in nearby galaxies moved. We will see how years of careful observations revealed these galaxies appeared to contain huge amounts of invisible mass, what we now call dark matter. The existence of dark matter fundamentally changed our entire cosmological model and spawned an entire new field within astronomy, focused on studying dark matter in the hopes of explaining what exactly it is and how it affects our universe. These questions tie back into one of the most fundamental questions that astronomers find ourselves asking. How did the universe begin? We think of the Big Bang as the beginning of the universe, but this story itself, from its name to its model of how the cosmos came to be, has its own interesting beginnings. Big Bang cosmology is now widely accepted as the scientific model for where our universe came from, but it also poses several ongoing mysteries. From what exactly happened in the earliest fractions of a second after the universe began, to the mysterious force known as dark energy that appears to be powering its continued expansion. Finally, where does the Big Bang ultimately leave us? Astronomers are still debating how the universe has evolved, the existence of parallel universes, and how our universe might end. In the second part of our discussion, we'll focus on Albert Einstein. His very name is synonymous with genius and discovery, and in this section of the course we'll consider some of the most mind-bending concepts in astronomy: gravity, time, black holes, and the extremes of light and energy that challenge our understanding of how our own galaxy works. It's tempting to think of astronomers as being concerned only with far-reaching challenges, like how the early universe began, the mysteries of deep space, and the physics of stars and galaxies many millions of light years away from our own home here on Earth. However, for the astronomers who study these questions, our scientific pursuits are inextricably tied to the people who study them. Many astronomers have, alongside their groundbreaking research in space, dedicated their time and energy to fighting discrimination and advocating for equal opportunities in astronomy and the broader fields of science. Another hero of astronomy is Oscar Duhalde, who became one of only a handful of human beings in history to make an exceptionally rare astronomical discovery. In 1987, Oscar, a telescope operator in Chile, became the only living person to discover a supernova with the naked eye. The distinction is a rare one, shared with Johannes Kepler in 1604 and Tycho Brahe in 1572, and Arabic, Chinese and indigenous North American astronomers observing the heavens in the 1050s. These discoveries made crucial contributions to our understanding of what supernovae are, how we work and how we study them today. Supernovae are incredible energetic events produced in the final moments of a dying star's life, events that emit energy across the entire electromagnetic spectrum, a fact of physics that can be easy to forget for those of us used to seeing the world through the narrow range of wavelengths detectable by the human eye. In fact, dying stars and many other objects in space emit radiation in the high energy regime of the electromagnetic spectrum, at energies so high and wavelengths so tiny that we need to invent new techniques or even leave Earth entirely in order to study them. These wavelengths include X-rays and ultraviolet light. Most of us think of X-rays as medical tools used to study our bones, and of ultraviolet light as the pesky thing that causes sunburns. In reality, observing X-ray and ultraviolet light from space can offer a fascinating window into things like newborn stars, enormous black holes, and even the workings of our own sun. Several pioneers of astronomy led the field in how to study this light, a particular challenge since it can only be detected from space. Years before the Hubble Space Telescope launched, visionaries like George Carruthers, Riccardo Giacocani, and Arthur B.C. Walker Jr. developed the cameras, technology and techniques required to capture this invaluable data from the cosmos. At the other end of the spectrum, radio telescopes also offered us the opportunity to uncover strange and exotic physics in space. In 1967, an astronomer named Jocelyn Bell discovered a strange signal, perfectly regular pulses of radio emissions, in data from a radio telescope in Cambridge, England. Her discovery proved to be the very first observations of something called a neutron star, the tiny and dense remnant left behind by the supernova death of a massive star. Neutron stars and their higher mass cousins, black holes, are some of the most extreme objects in the universe, and the astronomers who have studied them over the years have transformed our understanding of how stars, gravity, space and time work. Published in 1915, after 8 years of work, Albert Einstein's general theory of relativity connected the properties of gravity, space and time. In the years that followed, it fell to Einstein's fellow astrophysicists to seek out observational proof of this theory. In 1919, the astronomer Arthur Eddington found the first proof that Einstein's theory was correct during a solar eclipse expedition. 55 years later, after Jocelyn Bell's groundbreaking discovery of neutron stars, Russell Hulse and Joseph Taylor found more evidence for Einstein's general theory of relativity by closely observing a pair of neutron stars as they orbited one another. Combined, these observations have revolutionized our understanding of the fabric of our universe and the mysteries of gravity. One long-standing mystery of gravity was the phenomenon of gravitational waves, predicted by Einstein's theories in a mathematical result that drew skepticism even from Einstein himself. Gravitational waves are minuscule ripples in the fabric of space-time caused by the collisions of enormous black holes, but tinier than the width of a proton when they arrive at Earth. Gravitational waves were first successfully detected in 2015, the result of decades of effort by thousands of researchers to build and operate the most sensitive observatories on the planet. This discovery came about thanks to a combination of cutting-edge physics, exquisitely precise engineering, and the management of an immense team of thousands of scientists. Today, gravitational wave astronomy is an exhilarating new subfield propelled by this same large team of scientific heroes. With phenomena like gravitational waves, supernovae and other transient events happening all over the cosmos, it's become clear that astronomers need to keep a constant watchful eye, or many large eyes, on the sky. However, capturing a brief flash of a supernova or the motion of a tiny comet or asteroid across the immensity of the night sky is no small task. Since the 1960s, teams of innovative astronomers have taken on the Herculean job of surveying the entire night sky, using a diverse array of telescopes and tools to painstakingly catalogue everything that we can see. Early efforts included surveys of the northern sky using endless stacks of photographic plates and ongoing observations by large networks of amateur astronomers, willing to dedicate their backyard observatories to long and detailed studies of anything that might be changing in the night sky. Today, teams have launched space telescopes designed to observe every star in the entire Milky Way galaxy, and a groundbreaking new telescope in the southern hemisphere that will soon begin a 10-year-long campaign to continuously photograph the entire sky every few nights. With so many large and heroic teams conducting all-sky surveys and achieving marvels of engineering to study gravitational waves and put telescopes into space, it can be easy to imagine that the whole planet shares this dedication to astronomy research. That said, the big question of the universe can easily start to seem quite remote and small when faced with the many challenges of day-to-day life here on Earth. More than any other science, communicating the discoveries, importance and the wonder of astronomy to the rest of the world is a crucial role for astronomers if we hope to continue studying the cosmos. Carl Sagan was the first and the most famous astronomy ambassador of the modern age, and many other heroic efforts have been made to advocate for astronomy research and increase public enthusiasm for science. Sagan was also a specialist in studying our own solar system and imagining solar systems beyond our own. In this final section of our talks, we'll look at the science of our own cosmic backyard and learn about the heroes who are studying our potential neighbours in the universe. One clear and immediate connection between the mysteries of space and life on Earth are asteroids and comets, the small citizens of our own solar system that might one day come close, perhaps even a bit too close, to our home. Finding and studying nearby objects like these is a crucial part of understanding our solar system and the fate and history of our planet. Astronomers like Jean and Caroline Shoemaker built up a long and prolific history of discovering and studying comets and asteroids, along with their potential impacts. One dramatic example was observed by astronomers and stargazers all over the world in 1994, when comet Shoemaker-Levy 9 struck Jupiter. More recently, large survey and robotic campaigns have taken up the mantle, with teams of people monitoring the sky, searching for asteroids and comets throughout the solar system, and learning more about these fascinating little members of our solar system along the way. It's hard to talk about small solar system citizens without also thinking of Pluto, our little former knife planet, and wondering what exactly happened to it. The astronomical heroes, or maybe anti-heroes, behind Pluto's journey from discovery to demotion span more than 70 years. In 1930, Clyde Tombaugh discovered Pluto and classified it as the 9th planet in our solar system. In 1960, Julio Fernandez predicted that an enormous and crowded belt of smaller rocky objects should surround the outside of our solar system, just at and beyond Pluto's orbit. In 1992, David Jewett and Jan Liu discovered the first observational evidence of this belt. The research that followed ultimately led to Pluto's demotion from planet status in 2006, along with a significantly expanded picture of our solar system and its outer boundaries. At the heart of our solar system, our own Sun has also been an immense font of information about astronomy and the inner physics of stars. Solar physicists have used enormous tanks of liquid to detect neutrinos, tiny subatomic particles that emerge from the Sun's core and act as minuscule ambassadors from the immensely hot and dense heart of a star. Astronomers have also been mounting heroic solar eclipse expeditions, with observations carried out in some of the most remote corners of the globe to study gravity, magnetism, and the Sun's evolution. This fascinating array of techniques and creative ideas has allowed us to harness the scientific power of our closest stellar neighbour. For years, astronomers imagined other stars like our Sun potentially hosting other distant solar systems. In 1992, these imaginings became a reality. Alexander Wolszczan and Dale Frail announced the first discovery of 2 exoplanets, or planets orbiting another star. From this first discovery, astronomers have gone on to detect thousands of exoplanets, refining their observational techniques and building new space telescopes specifically designed to find these tiny and distant stellar companions. Today, teams of astronomers are working on discovering new exoplanets and exploring what new worlds might look like in planetary systems across the galaxy. Of course, studying distant planets also raises what may be the single most compelling question of all astronomy: are we alone? The search for life in space is an ongoing and fascinating pursuit within astronomy, and one that raises fundamental questions about the universe, Earth, and our nature as human beings. Astronomers like Vicky Meadows and Sarah Seeger have focused their efforts on the field of astrobiology, synthesizing 2 fields to better understand how life could begin to flourish on distant worlds. Others, like Jill Tarter, have turned their efforts towards SETI, the search for extraterrestrial intelligence, in the hopes of detecting intelligent life on other planets. Exploding stars, gravitational waves, alien life. The astronomical mysteries of today and tomorrow ask big questions, and answering them will require big telescopes, big dreams, and a new generation of astronomical heroes. In the next decades, enormous new ground and space-based telescopes will begin operating. These facilities are set to change the face of astronomy, offering new and powerful tools for observing nearby asteroids, strange stars, and distant galaxies. Innovation in astronomy also requires thinking far ahead, considering what the cutting-edge technology of the next century will mean for how we study the cosmos. Tomorrow's heroes of astronomy are already hard at work today, imagining new telescopes that will be decades in the making and unveiling new discoveries that will shape our future picture of the universe. Many of these same scientists also work hard to educate the next generation of researchers and spark widespread interest in astronomy, ensuring that humanity can continue studying the universe in the years to come. At this point you are likely to have many questions about the discoveries and heroes you have heard about in this first program. Who are the people that built telescopes for use on Earth and in space, and how are we using these telescopes today? Why did we need thousands of people on the team that detected the first gravitational waves? What might we expect to learn in the years and decades to come? During these programs we'll be delving deep into many of the topics we've touched on today, learning about the science behind these discoveries, as well as the many different people and types of heroes that have shaped our view of the universe.
Slight break in transmission. We should now be on the official stream that we've set up. Sorry about the technical problem there. Anyway, so yes, I mean the geology of this area is a history of billions of years, uninterrupted. So it will be really interesting to see what's there. That whole landscape is extremely, looks very strange and haunting and mysterious. You can see it behind me. But this is where NASA are planning to land Artemis 3 at the end of 2025. And as we were saying the other night, there are lots of other missions that are planned to land here as well. China, South Korea, other countries as well are planning to sort of zero in on the South Pole to investigate it and see if they can actually try and sample the water that is meant to be here, if all of the orbiting spacecraft have got it correct, which they seem to do. So here we are. So we're just a few minutes now before the landing. As you can see, mission control there in India, and I can see figures on a screen there, but I'm not quite sure what they represent.
Yeah, they've actually almost looked as though they've got a camera pointed at the moon.
Yes, it
in
does.
One of the screens there.
It does, doesn't it? In the middle,
yeah,
it looks like there's a camera pointed at the moon.
Yeah,
in which case, it's
moving,
still at some considerable altitude. I'm just trying to work out from those figures. There's a 30 there. Would that be kilometers? Maybe, I don't know. But also progressing well. Let's just listen in for a moment to see whether we can work out what's happening. Nothing much going on at the moment. Oh, they're clapping something.
जी हाँ, अब हम देख सकते हैं रफ ब्रेकिंग फेज की शुरुआत हो चुकी है।
During this rough braking phase, the lander velocity shall be brought down from 1680 meters per second to 358 meters per second. The altitude will be brought down from 30 kilometers to 7.4 kilometers at the end of rough braking. All this in the duration of 690 seconds or 11.5 minutes. Currently, the Laser Inertial Reference and Accelerometer package (LIRAP) is aiding in the navigation.
जी हाँ, अभी आप अपनी स्क्रीन पे देख सकते हैं कि लैंडर अब तक कुल 191 किलोमीटर हॉरिजेंटल दिशा
Right, so I was right. So that figure on the right is the
Yeah,
altitude. That's 30.48
yeah.
kilometers.
And the landing burn's underway. So
Yeah. Yeah, the landing bird has started.
oh, exciting stuff.
Yeah, there we are. You can see it there, 31 kilometers. Seems to be climbing.
Okay.
Now it's going. It's definitely climbing. Right.
Oops.
Yeah.
Well, we'll just give it time. It's probably all nominal, as they say.
Yes, it's probably all nominal.
So,
Well, it has survived this far, which in itself is a great achievement.
yeah, well, it's been quite a long project because it launched. When did it launch? Was it the 14th of July?
Yes, it was the 14th.
Yeah, launched on the 14th of July. It entered translunar injection was on the 31st of July. So it had been round, already for quite a long time. It took it a while getting there. And then since then it went into a very large elliptical orbit. And since then it's been performing lots of maneuvers, bringing it closer and closer to the, I was going to say the sun, the moon. So that's till we got to this position today. Hopefully, fingers crossed, everything goes fine for them. We need some good news. I can actually see on the screen there they've got what looks like lunar images.
Yes.
So they've taken this panel. Oh, there we are.
I'll just say that the actual trajectory from the Earth to the Moon was achieved by subsequently raising orbits of the Earth until the spacecraft reached the gravity of the Moon influence and the influence of the gravity of the Moon, and then slowly did more orbits of the Moon to get down to the position where they needed to be to do the landing burn. So it was all done through different, raising and lowering orbits, basically.
Yes.
Yeah, because that took 10 days.
Exactly.
It did five individual maneuvers, slowly, as you said, Michael, raising its orbit before it actually left the Earth's gravity on this way to the moon. So yeah.
So I suppose you could say it's an efficient way, but in fuel wise, if you like, but not in time.
Yeah, it's definitely coming down now.
Yeah, you can see that now, coming down quite nicely.
Yeah.
With the horizontal velocity decreasing.
Yeah.
And the vertical velocity, of course, increasing as it descends.
Yeah. That's in meters per second.
Yes.
So it's moving at quite a bit of a speed at the moment.
Absolutely.
But,
if you look at the graph, it's about to start the real descent.
I like the way on that image just then it said rough braking.
Yeah.
It's like it's thrown out an anchor or something.
Yeah.
Is that the proverbial anchor?
Yeah, absolutely. Absolutely. Yeah, it's sort of, how much are we going to deaccelerate it? Oh, I don't know. It's just roughly, whatever, 200 meters per second or whatever, or 50, up to you, really. So, rough braking. But that lovely image on the left of the approaching moon.
Oh, yeah.
That's lovely, isn't it?
Yeah, that's nice.
Very reminiscent of.
Nice to see. Nice to see.
Very, very reminiscent of Apollo, isn't it?
Isn't it just?
Yeah. I mean, because the images when it actually reached the moon and it did its first flyby,
Yeah.
they were crystal clear. They were
They
fantastic.
were.
We are spoilt now with the cameras that they use today.
Yeah.
I'm saying that actually, I watched the Russians launch the Progress mission to the International Space Station last night, and the cameras to say, I think they're still using Zyka or something like that. The images were there. You could see what was going on, but they weren't that good. But yeah,
They're probably ex shopping centre security cameras. Or...
yeah, probably Zenit E's.
Yeah. There's nothing. No, don't diss the Zenit E.
It was a good camera as long as you could lift it up.
Yeah, it was substantial. You could drop it and it would survive.
Yeah, made of old tank parts.
Exactly. The Helios lens on the Zenit E was a phenomenal lens.
Yeah. I'm not knocking it. I'm just saying, but if you could lift it up to your eye, and well done.
Right.
You realise you're showing your age now, don't you?
Who cares?
Oh well, yeah.
Who cares? Those poor kids who never experienced Russian technology like that.
Yeah, and film even.
Yeah, exactly. Yeah, no, it was good.
Ian's asking in the chat who's filming the video of the lander. I think it's Ridley Scott.
Yeah.
Yeah,
I haven't had a look in the chat. Hi guys. Hello Graham. Hello Ian. Hello Astronobulae. Nice of you to join us.
Steve's there as well.
And Steve's here. Yeah, Steve as well.
Gerard's here as well in the world. Hello, Gerard in the world. Hoping weather's good. Facebook user says, I came upon this by accident. Very lucky. Well, we are so glad that you did, Facebook user. And don't forget, if you want to tell us your name, you'll have to do so in your messages because we just see you as Facebook user, unfortunately. And we'd rather be a little less formal. Mm-hmm. So here we are. So we're just in the final, well, not the final approach. How long have we got to go? Still about 25 minutes. So plan to launch about 1:45. Aren't they? Plan to land about 1:45. Is that what I think?
Landing touchdown is in 16 minutes. Yeah, 16
minutes.
So it says here, but
yeah,
that could be out of date actually because I think my thing's frozen. So that's enough.
Roger says he can't use his telescope from Sparkford as moonrise is still 30 minutes away. Yeah. Yeah, very good. I bet it's a clear sky in Sparkford, as always. Yeah. So thank you all for joining us. It's great to have you with us twice this week. So fingers crossed for a successful landing. Lovely image of the moon there. Look, it's not a video, as you can see. It's updating every so often. So it's not an actual live feed. It's a camera.
Yeah. So sorry, I've got to correct myself. It's 11 minutes to touchdown. Sorry.
11 minutes to touchdown.
Yeah.
Wow. Yeah, 16.6. It's down to 16.5 kilometers now. And we will join the commentary from ISRO just in the final couple of minutes, I think, just to listen to what they say. Let's hope it's a we're down, hurrah, rather than a whoops. Because I would not have liked to have been in the Russian control room last week when Luna 25 was lost. That must have been dreadful.
No.
So,
I mean, I'm not. It probably wasn't, but the whole thing seemed to be quite rushed.
Yes.
I don't know. It's very, very sad. Those people have put a lot of work into that. And space is one of these. No matter what the geopolitics is happening in this world, but space is one place where everybody comes together. So. It's one of these things that it can bring people together. Geopolitics put aside, and so we like I said, we are sad for what actually happened. We want people to succeed. So
we do.
Yeah.
And the other thing is, of course, what actually happened with the with Luna 25 was that they fired its engine to put them into the final configuration of orbit, if you like, before landing, and the main engine should have fired for 84 seconds, and it actually fired for 157. That's what actually happened, and they couldn't turn the main engine off. So when they did get it off, it had accelerated the spacecraft and accelerated it towards the surface of the moon.
Yeah.
Very sad.
I don't know what you're posting, Michael, but I've got to review your message, so better not be naughty.
Never.
Right. So let's now join the Indian Space Research Organisation. Let's listen to the last few minutes of their commentary.
Yes, we are privileged to have with us Honorable Prime Minister of India, Shri Narendra Modi ji, who has joined us from South Africa's Johannesburg to encourage us.
Well, that's nice.
Yeah.
जी हाँ, आप ये देख सकते हैं एल्टीट्यूड होल्ड फेस भी बहुत ही आसानी से लैंडर फेस ने पार कर लिया है और अब फाइन ब्रेकिंग की शुरुआत हो चुकी है। अभी हम ये देख सकते हैं कि लैंडर की ऊंचाई लगभग 5.6 किलोमीटर है, जो कि इस फेस के उपरांत लगभग 800 मीटर हो जाएगी।
Okay.
Right.
We can hear from the mission operations team that the sensors are performing nominally, and we are currently in the midst of the fine braking phase, which is going to continue for 3 minutes, and the altitude is going to be reduced to nearly 800 meters at the end of this phase.
Gosh.
जी हाँ,
Crucial
जैसे कि
time.
आरुषि जी ने बताया
Yeah.
कि लगभग 3 मिनट के उपरांत लैंडर की हाइट लगभग 800 मीटर वर्टिकली होगी और यहाँ पे लैंडर की हॉरिजेंटल वेलोसिटी, वर्टिकल वेलोसिटी, इवन डाउन रेंज भी लगभग शून्य होगा।
Because it was about this time that they lost Chandrayaan.
We can see the visual of the
Yeah.
lander module, and we can see that the downrange traveled is nearly 831 kilometers.
Yeah, because of course none of this is easy.
No, it's-
Was it the Japanese who lost theirs? And it was due to the ground radar. It passed over a big crater,
आप
and
अपनी
all,
स्क्रीन
so
पे
it was
देख
reading the
सकते हैं
surface,
कि
and
लैंडर
then of
की
course it
ऊंचाई
dropped away,
अब चंद्रमा के सतह से लगभग
Yeah.
3 किलोमीटर से कम हो
and it
चुकी है।
thought it was higher than it really was.
it's very
So
sad. But
We
we're
are
down to 2
very
kilometers
close to
now.
the moon's surface, nearly 2.6 kilometers, as we can see.
Very
yeah,
exciting.
I'm looking at those craters on those images.
Well, it seems to be coming down between them, which is good. Look, it's definitely over,
Yeah.
not over a big crater. I'm going to be really interested to see exactly where the landing site is.
Yeah,
So I can find it on the map. The Prime Minister
he looks a bit stern, doesn't he? Yeah, he looks a
आप
bit
देख
stern.
सकते हैं कि लैंडर की ऊंचाई लगभग 1 किलोमीटर के आसपास है।
1 kilometer coming up or coming down. Nail biting stuff.
We are nearing the final phase of the power descent, which is going to be the vertical descent phase or the local navigation phase.
Now this is where it gets tricky.
Yeah.
जी हाँ, अब हम फाइन ब्रेकिंग वेव के एकदम करीब आ चुके हैं। हाँ, आप तालियों के गड़गड़ाहट से सुन सकते हैं कि हम लोगों ने तीसरे चरण को भी बहुत ही सफलतापूर्वक हासिल कर लिया है और अभी हम वर्टिकल डिसेंट फेज में आ चुके हैं, जिसकी शुरुआत भी बहुत ही अच्छे ढंग से हो चुकी है।
Yeah. Let's get back to the telemetry, please. Vertical descent.
A lot of applause indicates that till now the performance has been nominal. We are in the vertical descent phase 1. The altitude is being brought down from 800 meters and we are nearing and approaching the lunar surface.
जी, आप अपने स्क्रीन पे देख सकते हैं कि लैंडर का हाइट लगातार कम होता जा रहा है। इस समय हम लैंडिंग साइट के जस्ट ऊपर हैं और इस समय इसकी ऊंचाई लगभग 600 मीटर के आसपास है। इस फेज के दौरान लगभग 150 मीटर के ऊंचाई पे पहुंचने के बाद
Ooh, 100
लैंडर
meters.
अगेन लगभग 20 से 22 सेकंड के लिए हॉवरिंग करेगा।
I think that image on the left looks about.
We are above the landing site. The horizontal as well as the vertical velocity is now being constantly reduced, and the lander module has begun its descent towards the landing site.
It's only 8 meters a second now, vertical.
Yeah.
So. Ooh.
जी हाँ, आप अपने स्क्रीन पे देख सकते
6
हैं
meters a
ये जो
second.
पथ
5
निर्धारित
meters.
किया गया
So
है,
it's
लैंडर
slowly.
पूरी तरह से उसी को ही फॉलो कर रहा है। इस समय हम लगभग 200 मीटर की हाइट से भी कम आ चुके हैं। अब हम ये देख सकते हैं कि हम लगभग 150 मीटर की ऊंचाई पे हैं चंद्रमा के सतह से।
That's not looking good. The vertical velocity is dropping off.
We are approaching the vertical descent phase 2, which will have the lander module hovering
It's
at
hovering.
nearly
That's
150 meters above the
जी
lunar
हाँ,
it's hovering.
surface.
जी हाँ, आप इस तालियों के गड़गड़ाहट को सुन सकते हैं, जो कि सेकंड हैवरिंग फेज के कंप्लीट होने के बाद इन
I
सारे
was worried.
वैज्ञानिकों के
I thought they were
It's
going to go.
retargeted.
But I thought they were going to go into negative figures then.
Yeah.
जी हाँ, आप अगर फिर से ध्यान से देखें तो एल्टीट्यूड पुनः
Oh,
कम
that's
होता जा
very
रहा है।
slow.
अभी हम लोग लगभग
2 meters a second.
135 मीटर की ऊंचाई पे हैं।
Oh, they're taking it very.
The sensors that are updating at this point are providing confirmation of the safety of the landing site.
As expected, the retargeting is going on, and this is a very good signature for the lander. अभी आप ये देख सकते हैं कि लैंडर की ऊंचाई लगभग 65 मीटर के आसपास बची हुई है।
I see we have Dave Galvin in the chat. Hi, Dave. Nice to see you.
Currently,
Hi,
only 2 engines are now being fired, and we are nearly at zero velocity, vertical and horizontal. We were hovering, and now we are approaching the moon's surface.
Right, so they've
Wow.
धीरे
retargeted.
धीरे
All
लैंडर
your
की
crater away.
वेगमान को कम किया जा रहा है
So they're
और
now
हम अब
descending
लगभग
again.
50 मीटर से भी कम आ चुके हैं।
Very, very, very nice manoeuvres being carried out here.
We can see the Honorable Prime Minister,
Very delicate,
Shri
isn't it?
Narendra Modi
Very
ji,
delicate.
who is here to encourage us, and he is critically looking at the visuals.
Go Chandra. Go
Left
Chandra.
a bit, left a bit, left a bit. Up your end, down a bit.
जी हाँ,
It's
आप
there.
अपनी स्क्रीन पे देख सकते हैं
It's there.
कि हम लैंडर मॉड्यूल
India have successfully landed at the south pole of the moon.
People are applauding. Let
लैंडर
us all
मॉड्यूल
wait to hear from the Secretary Department
wait
of
the flag
Space and
for-
Chairman ISRO, Shri S. Somnath.
Can they got him a bigger
लैंडर
flag?
मॉड्यूल पूरी तरह से
Yeah.
सेफली और सॉफ्टली चंद्रमा के सतह पे लैंड हो चुका है। ये हम
Well,
लोगों के लिए
congratulations.
बहुत ही गर्व की बात है। हिंदी में एक कहावत है,
Okay, congratulations to India then, because they have landed at the south pole of the moon, the first spacecraft to do so. This is a momentous day for India, so congratulations to everybody.
Yeah,
And
well
it's a
done.
momentous day for the exploration of the moon, because, as I said, nobody's ever done this before, and the south pole of the moon is an exceptionally
Yeah.
interesting place.
And actually, Dave's given us some technical information here. He says those graphics are done on a Spectrum computer.
They probably were, Dave. Yeah, they probably were. Yes, indeed. So, yes, Kevin, you're quite right, saying the Indian PM could have got a bigger flag. But Ian says, well, he's got 3 flags behind him. So, there we are. So, many congratulations. Let's listen to, let's see if this commentary is in English now.
मेरे प्यारे परिवारजनों, जब हम अपनी आंखों के सामने
Obviously not. So, so there we are. Great. Well, the next step, of course, will be to deploy the rover onto the surface of the moon so it can start doing scientific work. We will find out exactly where it landed, I'm sure, at some point today. And we'll show you that in our Monday live stream next week.
Yeah, do we want to quickly run through what this little rover will be looking at, Andy?
Absolutely. Go for it.
Yeah, it's of a 6-wheel design. It's like the old Tyrrell Formula One car. It's 26 kilograms, so it's quite light. We could lift that. And it has a range of 500 meters. I won't go into all the dimensions and all that, but it's going to be looking at the composition of the lunar soil.
Yeah.
So that'll be the regolith. The presence of water ice in the lunar soil. It'll be looking at the history of lunar impact. So it's going to be looking at the craters and probably doing some spectroscopic analysis or mass spectroscopy stuff. So, and the evolution of the moon's atmosphere, because as we said, we all say the moon hasn't got an atmosphere, but it's got a very, very thin one. There is actually an atmosphere there, but it's very tenuous. Yes. So, but that's what it's going to be looking at. And as I said, I want to get down to the geology and have a look and see what's underneath all this regolith. So,
yes, definitely. Will the rover be actually able to dig much into the regolith? Does it say?
I honestly don't know, because I'm just looking at the design. I can't see anything like a shovel or a pick. So, yeah, they haven't sent any navies up. So,
no.
Yeah.
Well, perhaps
hopefully we'll be able to glean some, because with the impact craters, the crust is going to be stirred up anyway, so it's going to be in some in the regolith and that anyway. So we should get a good idea of what's there. So yeah, well, congratulations! It's good. We've actually had a success. That's nice. I love it.
Yeah, I know. After the loss of Luna 25 last week, this is a really big step forward for the study of the moon. And I bet the Russians are feeling a bit pig sick now watching this. So commiserations to the Russians.
Well, it's as you said on Monday, the Russians have, with not just because of that failure, they've said that they've really got to go back to basics and totally redesign. I did see a image of then what they're building as a new capsule, and it's totally different. It's almost a bit like what SpaceX are using. It's a far more modern design because, of course, when the fairing comes off of the actual rockets, you've got that big round bulbous thing, which is the cabin. Yeah, but they're going towards the more traditional what we see with the Americans and everybody else. So they're going back to the drawing board and they're going to start from scratch. And more power to their elbow. Let's just hope they can sort themselves out.
As ever, it's the money, and the Russian space program, as much as any other sector of the Russian economy, is of course being hit largely by Western sanctions at the moment. So, perhaps that will improve once.
Yeah. Well, they relied upon a lot of Ukrainian. A lot of the components were made in Ukraine.
Well, indeed.
And of course, it's the same for the Western countries, because they get a lot of manufactured goods from Ukraine, and of course, it's affected the British space industry because a lot of the technology was coming from Ukraine. Absolutely. And then it all kicked off because we probably would have had launches already. But saying that, we haven't got any launch pads ready yet, so maybe not. But yeah, so it's if we can get ourselves sorted out, then hopefully we'll be launching soon. But we've got a lot of exciting times to come.
We've got a lot of exciting times, and we'll cover them all here on Space Oddities for you, of course. So let's just have one final listen to the commentary to see if there's anything happening in English, whether there's an interpreter. Just give me 1 second, and we will find out. No is the answer to that. So, so there you are. So I think that will just about bring our broadcast today to a close. Thank you so much of you who've dropped in to watch this. I see we've got 39 people watching at the moment. So that's very good of everybody to watch.
Yeah, for a Wednesday afternoon.
For a Wednesday afternoon, that's wonderful. Next Monday, we have as a very special guest the astronaut Scott Potteet, who is the pilot of the upcoming Polaris Dawn mission, which is due to launch no earlier than last quarter this year. An exceptionally pioneering, innovative space mission. Find out all about it on Monday when Scott joins us. If you have any questions for him, of course, you're more than welcome to ask. And we will look forward to having Scott as a real-life astronaut as our guest. He was originally meant to be with us in July, if I remember rightly, but due to one commitment or another, he's been unable to. So we're hoping he's able to join us next Monday, and we should look forward to receiving him as our very special guest. It should be really interesting. So we'd like to thank you all for being with us this afternoon. Many congratulations to India for a spectacular and safe landing on the south pole of the moon. Can't wait to see the images, and they should be absolutely epic, and we will find out before then exactly where it landed.
Just before you go, Andy, Astro Nebula says, looks like you've aged a bit, Andy, but I like the three flags behind you.
Well, Astro Nebula, this is what spaceflight coverage does to you. It gives you premature aging. So yeah, let's just kill that. So that's a bit close as well. So let's put us back. There we are. So yeah, thanks guys. Thanks a lot for being here. We do appreciate it. Wonderful.
Yeah, nice seeing you all.
And nice seeing you all. And we will see you on Monday with the astronaut Scott Potteet. So take care of yourselves. Have a fantastic week and weekend. And we'll see you on Monday, 8 o'clock UK time, as always.
Yeah. See you all.
Bye for now. Keep looking.
Okay. Thanks, Andy. Yep, this is Euclid, the next European Space Agency Space Telescope, as Andy said, subtitled Exploring the Dark Universe. Okay, I'll do that. So, what is Euclid? Euclid is a visible to near-infrared space telescope developed by the European Space Agency and the Euclid Consortium. Euclid is named after the Greek mathematician Euclid of Alexandria, who lived around 300 BC and reported to be the founder of the subject of geometry. As the density of matter and energy is linked to the geometry of the universe, the mission was named in his honor. That's where the name comes from.
All right.
And the way Euclid came about, previously there was two missions proposed under ESA's Cosmic Mission 2015 to 2025. The first one was Dune, the Dark Universe Explorer, and Space, the Spectroscopic All-Sky Cosmic Explorer.
They work so hard on these acronyms, don't they?
Yeah, exactly. Both missions proposed complementary techniques to measure the geometry of the universe, and after an assessment study phase, a combined mission resulted. Euclid was selected by ESA's Science Programme Committee for implementation in October 2011, and in June 2012 it was formally adopted. So that's how it came about.
Right.
So the mission is to explore the composition and evolution of the dark universe. The Space Telescope will create a great map of the large-scale structure of the universe across space and time by observing billions of galaxies out to 10 billion light years and across more than a third of the sky. Euclid will explore how the universe has expanded and how structure has formed over cosmic history, revealing more about the role of gravity and the nature of dark energy and dark matter. Okay, the construction, the Space Telescope was built by Thales Alenia Space in Italy. And Euclid is 4.5 meters long with a diameter of 3.1 meters and a mass of 2,160 kilograms. Okay, just a little bit of science, not a lot, because I don't fully understand it myself. So what is the dark universe? Well, scientists, apparently astronomers and scientists, think that we can only see 5% of the actual universe with the visible instruments, our eyes, and other instruments in the electromagnetic spectrum. We can only see 5% of the universe. So 95% of the universe is unknown or dark, and that's where we get the commonly known sorry about that. Commonly known as dark matter and dark energy. That's where we get that from. Okay. So 5 mysteries Euclid will help solve. What is the structure and history of the cosmic web? What is the nature of dark matter? How has the expansion of the universe changed over time? What is the nature of dark energy? And is our understanding of gravity complete? Okay, Euclid, or more about Euclid itself. Euclid will be launched on the SpaceX Falcon 9 from Cape Canaveral Space Force Station, I believe on the 1st of July. And originally, Euclid was going to be launched on a Russian Soyuz rocket, but this was changed after the recent invasion of in Eastern Europe, and then Russia, that was cancelled for that particular flight. But this is now being taken up by SpaceX. There's 2 science instruments, the visible wavelength camera, or VIS, and the near infrared photometer and spectrometer called NISP. The Euclid Consortium has delivered to each of the VIS and NISP instruments, and NASA provided the near infrared detectors of NISP. Okay. Euclid will observe a third of the sky. It will measure the shape, position, and distance of galaxies up to out to 10 billion light years. It will create the largest, most accurate 3D map of the universe ever produced. Okay, so Euclid will address 2 core themes of the ESA's Cosmic Vision 2015-2025. What are the fundamental physical laws of the universe? How did the universe originate, and what is it made of? Okay.
Yeah, but are they going to explore anything important?
Don't matter.
Those are small questions, you know. Get real.
Yeah.
Okay.
Right.
So Euclid isn't a large telescope, as space telescopes go. It's a 1.2 meter diameter mirror, and the spacecraft itself is only 4.7 meters tall and 3.7 meters in diameter. I think, as you can see from the previous slide, it's the actual instruments that are doing the work, of course, and that's where we're going to get the science data from.
So the actual mirror is only 1.2 meters.
1.2 meters, yeah.
Yeah.
So the visible instruments measures the shapes of billions of galaxies between 550 and 900 nanometers wavelength. It has a mosaic. This is what interests me. It has a mosaic of 36 CCDs, or charge coupled devices, each one giving 4,000 pixels each. So each CCD has 4,000 pixels on that particular detector. The near-infrared spectrometer and photometer measures the brightness and intensity of light from the galaxies, and is used to calculate the redshift stroke distance. And that works at between 900 and 2,000 nanometers wavelength. And that detector has a mosaic of 16 detectors, each having 2,000 by 2,000 pixels each. That will be the largest infrared field of view from space. I haven't actually checked that against James Webb.
It's a lot wider field than James Webb.
Yeah,
it's a lot wider.
So that still stands.
Yeah,
good. Okay. So Euclid will be stationed at Lagrange point 2, and it will actually be in the same orbit as the James Webb Space Telescope and ESA's Gaia Space Telescope. Launch, as I said, will be on the beginning of July. Excuse me, and it takes about 4 weeks to actually get to L2, much like the James Webb did.
Right. So they're going to be neighbours.
They are going to be neighbours. So just like the James Webb Telescope, Euclid has a large sun shield because obviously it wants to look in the opposite direction to the sun and the Earth. So this is just a slide showing the number of countries involved in Europe. So the list of countries there, obviously Germany, Italy, Spain, Portugal, and of course United Kingdom. So we're providing quite a lot of the expertise for the mission. Beyond Europe, we have the United States. NASA is providing some of the detectors, instruments for the spacecraft, and of course SpaceX who are providing the launch.
I love the involvement of Spain in this.
Okay.
Look at all the other countries. It's space this, space that, space this, and in Spain it's the Ministry of Economy and
Competitiveness. I thought that was good. Yeah.
So, because I don't think there isn't a national space agency in Spain.
Okay.
So there we are.
To create one.
Yeah, got to be competitive with these dark energy surveys, haven't we?
Yeah. Okay. Now this picture here just shows the size of the spacecraft.
What a beauty! What a beauty! Look at that.
Yeah, I know. This is actually an engineering test model. Which will stay on the ground. It seems a shame to build something like this and not send it into space to me, but
perhaps it'll end up in a museum somewhere.
Yeah, hopefully. So and you can see the size of the spacecraft compared with the people, the technicians working on the floor.
He's having his lunch.
Yeah. Now you might recognise this ship. This ship carried Euclid from Italy to Florida in the MN Colibri. It's also carried the James Webb Space Telescope from Europe and to South America to Kourou for its launch. It's done a lot of work for a space program recently. And that is how it was transported in that big container. And that is at Cape Canaveral Space Force Station. Okay, as I said, it will launch on Saturday, the 1st of July at 4 p.m. our time, which is a nice time of Saturday. So we may be able to have a live launch for that. And just so for those that may not be familiar, it will be launched from Space Complex 40, which is to the south of the Kennedy Space Center on the Space Coast. Right at the bottom of this slide here, you have the Space Launch Complex 40. 41 is there. The Launch Complex 39. With Launch Complex 39A, which SpaceX used for their crewed launches, and their rocket launch, their rocket assembly facility is near there on the old crawlerway. And just at the top of the slide, you can see Launch Complex 39B, which is where future space launch systems will launch from.
Great.
And just a minor one. This is the route that the rocket will take to take it into orbit before heading off to L2. And as you can see, a little blip out in the Atlantic Ocean. That is where the drone ship is. That will be that will catch the booster for landing. Okay, and if you want to know more, there's a website there. You can put this in the chat if you like, but there's plenty on the ESA website about that, about the mission. If you want to, if you want to find out more.
Now, the European Extremely Large Telescope is taking shape in the Atacama Desert in Chile, not too far away from where the European Southern Observatory have the Paranal Observatory, which is home to the world's most amazing telescopes at the moment. And I just thought that we'd just do a little bit about the ELT. Why at the moment? Well, because they've just released a new photograph of the observatory under construction. And they don't tend to release these photographs very often. Perhaps they think nobody's interested, but they don't tend to take that many photos of the ELT under construction. But they've released a new one this month, so I thought that might be a nice opportunity to have a look at the what will be, when it's completed, the world's biggest ever telescope, and this being the European Extremely Large Telescope, the world's biggest eye on the sky. Now, as I said, it's being built in the Atacama Desert in Chile, and it's built by the European Southern Observatory as a dazzling new future, and it's being built at Cerro Amazonas in Chile. And just to let you know where it is, that's the Paranal Observatory. There, you can just see the domes on top of the mountain there. And this is what it looks like. There's the famous Paranal Observatory. And Amazonas is not a stone's throw, but it's not that far away. So this will be where the ELT will be, is being built at the moment. Now, just a bit of data about this telescope. It has a main mirror of 39 meters. Originally, the mirror was going to be 42 meters, but Europe discovered that if they dispensed with the outer ring of the mirror segments, because there are currently 798 mirror segments in the main mirror, if they did away with the outer ring of segments and cut the diameter of the mirror from 42 down to 39 meters, they could save nearly €1 billion. So that's what they decided to do. As it stands, the telescope has a collecting area of 978 square meters. Now, all of those 798 mirror segments have to be aligned absolutely perfectly. The tolerance to which they have to be aligned is tens of nanometers, 10,000 times thinner than a human hair across the whole of the mirror. So that is an unbelievable accuracy that they have to achieve. And they have 4,608 sensors across the mirror measuring the relative positions of those segments and correcting them in real time if any get out of alignment. And the primary mirror weighs 132 tons. It's made of a glass ceramic compound called Zero Dura. And the total weight of all the mirrors is 140 tons. So this is a huge project that Europe has undertaken to build the world's biggest telescope. Now, let's have a look at the science goals of the telescope. Firstly, it's going to be used for imaging exoplanets directly and analyzing their atmospheres. And this has never been possible with an earthbound telescope before, but the exquisite light gathering power of the ELT will be enough to enable it to see exoplanets directly and analyze their atmospheres, much as the James Webb is doing at the moment with some of the exoplanets, as we were hearing recently from Roger about the TRAPPIST system. And this is the first time in history that technology of an earthbound telescope has been able to do this. The whole telescope is reckoned to have a resolution 15 times greater than the Hubble Space Telescope. So it just goes to show that putting telescopes in space is a great idea, but the technology for ground-based telescopes has caught up so much that the ELT will have an expected 15 times the resolution of the Hubble Space Telescope, and thus enable it to look at exoplanets directly. In terms of the solar system, well, it's going to be doing extensive survey work in the solar system and probing, among other things, the Kuiper Belt, other rocky objects, and it's going to enable us to see objects in the solar system with a telescope in far greater detail than we've ever managed to see before. The observation of stars is going to be important as well. The ELT will embark on a program of helping us to understand more about the birth, life, and death of stars, and also the link between the evolution of stars and the elusive dark matter. And that hopefully will enable us to answer some fundamental questions. Talking of dark matter, the ELT will also be used to find or identify what the dark matter is. I won't say find, because we know exactly where the dark matter is, but we don't know what it is. And as we were saying last week when we were talking about Euclid, the universe is only 5% made up of matter that we can see and measure directly. The rest of it is this so-called dark universe of dark matter and dark energy. Also, the ELT is going to be used to probe some of what are considered constants in the universe, the so-called physical constants. And they want to use the ELT to try and test whether some of these constants that the astronomers and astrophysics use are actual constants or whether they vary over time. So that's some pretty fundamental work that it's going to be doing on those. And of course, expect the unexpected, because they will undoubtedly be things that the ELT discovers that we had no idea were there at all. So that's a big science program ahead of the ELT. Let's look at the telescope itself in a little more detail. The telescope is made up of a 5-mirror system. As we said, a 39-meter segmented mirror of 798 fragments, then a 4.2-meter diameter secondary mirror that the light goes to next. Then there's a thing called a tertiary mirror, which is 3.8 meters in diameter. Then it goes to a 4th mirror, which is a flat mirror of 2.4 meters. Then it goes to a 5th mirror, measuring 2.7 by 2.1 meters. And then the light exits to the right of the telescope to the science instrument platform, where there will be lots of very, very advanced scientific instruments used to analyze that light. So it's quite a complex optical system, but this is what the astronomers and the engineers have come up with.
Sounds like a complicated collimation job.
Yeah, I would think so. Yeah, I hope they've got a laser or something handy to collimate that. And if you want to know what a 39-meter mirror actually looks like, they've done using these sort of cardboard hexagons. They laid this out to show you just how vast that primary mirror actually is. That's quite an amazingly large mirror.
Amazing.
And if you want to know how big the observatory will be, well, this is the observatory compared to Big Ben. So as you can see, it's big, and if you want to get a comparison for landmarks in your country, go to the website of the European Southern Observatory, and they've got the observatory compared to lots of other landmarks around the world. But as you can see, it's going to be it's going to be absolutely enormous. Here's a very short video where we fly into the ELT by the wonders of computer graphics. And I just think this is going to be like a huge cathedral of astronomy. That's the only way you can describe it. It's the size of a cathedral. So let's take a flight into the ELT. Okay, so that was a flight into the ELT. Sorry if that video was a bit jerky in places. The first step in building this massive observatory was blowing the top off a mountain and lowering the top of the mountain by 40 meters to create an area to build the observatory on. This happened on the 19th of June 2014. So that was the explosion blowing the pointy bit off the mountain. And then the top was flattened. The access road up to it was built, which obviously took a while. And the foundations were dug by October 2018. Then the foundations, the steel rebar for the dome and everything was put in September 2000, by September 2019. This was the picture in January 2022. The whole project, of course, got delayed by the COVID epidemic. So work had to stop for a while. But as you can see, by January 2022, they were making good progress. And this was November last year. And then the most recent photograph from the site, taken this month, you can see that they've moved on astoundingly well. So this is what the ELT now looks like. And the first light of the telescope, because of the delay for COVID, it was originally going to be 2025. It's now set for 2028. So there you are. So that is the extremely large telescope. And it's stunning, guys, isn't it? I mean, the sheer scale of it is just absolutely unbelievable.
Yeah, as you say, I'm just imagining because it's got that adaptive optics thing within it, where all the mirrors have got actuators underneath them, and they fire a laser into the sky, and of course it adapts to what the actual atmosphere is doing so fast. Yeah. I mean, it's an amazing piece of kit. It's absolutely fantastic.
I did a little calculation from what you were saying about Hubble resolution.
Yeah.
And it turns out that with the adaptive optics, it will have a spatial resolution of 0.00093 arc seconds.
Wow.
Well, that's not very good, is it?
We could do better.
Never satisfied, Daz.
There's always room for improvement.
Can you compare that?
Andy?
Sorry?
You were talking about the outer mirrors that taken to make it 39 meters, and there was another telescope called the Overwhelmingly Large Telescope.
Yeah, the OWL. Yes.
OWL.
Yeah.
Like the acronym.
Followed by the ridiculously large, the RLT. Isn't that?
Yeah.
I always thought
Shouldn't the OWL one be at Hogwarts?
Oh, very good.
Very good. I always thought they should have made one called the Superb Owl or Super Bowl. So that would have been good. In terms of resolution, Luke, can you compare that angular resolution to something? What was it for the James Webb, for example? Anybody remember?
James Webb is, of course, it's wavelength dependent, right?
Yes, of course.
Right? But the number that's often given, I think, is 0.032 arc seconds. So, and Hubble would be 0.014. Actually, a little better, but again,
it's wavelength dependent.
Wavelength dependent, yes.
Yeah, sure. There we are then. So, we're looking forward to the ELT. Can't wait to see the results from that. As I said, it's going to see first light now in 2028 if all goes well. I would love to have that on my bucket list, to pay that a visit, just to stand in that dome. I mean, can you imagine what it must be like?
I'll come with you, Andy.
Yeah, well, that's it. That's a date then, Michael. We'll do it.
We need more coffee money.
Ian says he can't.
Lots of coffee money. For
Ian
that.
says he can't wait till the BLT.
Ah, yes, absolutely. Yeah. So
the BLT. Ian wants a BLT.
So, if you're wondering, viewers, how that whole adaptive optics system works, see, the thing is, up in the high atmosphere, there's a layer of sodium atoms, and if you shine a laser at the sodium atoms, they fluoresce under laser light, and in the sky it looks like an artificial star. Now, the big problem with telescopes, as we all know as astronomers, is that the atmosphere never stands still, that it's got currents of air moving about continuously, which spoil the viewing. So there's another small telescope which will look at those artificial stars, and the ELT will have 8 lasers, so it will create 8 artificial stars, and they will be monitored in real time, and the movement of the atmosphere counteracted by applying a signal to each of the actuators that are behind each individual segment of that mirror, and they will move in the opposite way to what the atmosphere is doing, thus cancelling out the movement, which will give you an ultra stable image, even if the atmosphere is quite turbulent. Welcome to another in the series of Astronomy Basics videos from Space Oddities. In this video, we'll be asking the question, what is a galaxy? Just as the Earth's population is clustered into cities, so stars cluster in galaxies. They are the cities of the universe. A galaxy is an immense metropolis of stars numbering millions or billions. There are an estimated 2 trillion galaxies in the universe. Between the galaxies there is just cold, dark, empty space, devoid of stars, stretching for perhaps millions of light years in every direction. Stars in a galaxy, like the one shown here, orbit its centre, held in the eternal grip of gravity. Galaxies themselves may also cluster, as shown here in this NASA image of Stephan's quintet, a galaxy cluster imaged at infrared wavelengths by the James Webb Space Telescope. Gravity draws the galaxies together into complicated dances. As with skaters on a packed ice rink, collisions are inevitable. However, the encounter takes place over millions of years, during which time the galaxies slowly merge to form one single giant galaxy in a series of elegant dances choreographed by gravity. All these images show galaxies at various stages of merging, pulled into twisted, distorted shapes by their mutual gravity. While these might seem like giant cosmic catastrophes, in reality space is so vast and the distances between stars so enormous that collisions between individual stars are extremely rare. Galaxies are so tenuous that galaxy mergers are like clouds passing through one another. It was the great American astronomer Edwin Hubble who, in the 1930s, was the first to attempt a systematic classification of galaxies based on what he observed. His resulting diagram, shown here, is sometimes referred to as the tuning fork. Hubble classified galaxies into 3 main groups: ellipticals, spirals, and barred spirals. We now know that there are other types of galaxy, but the vast majority of galaxies in the universe fall into one of these 3 categories. Today, Hubble's tuning fork diagram still serves us well as a basic categorization of galaxies. So let's talk about one of Hubble's main classification of galaxies, the spiral galaxies. This archetypal classification of galaxy consists of 1 or more spiral arms of stars sweeping out from the centre like the arms of a Catherine wheel. At the centre of the galaxy is a bright core of stars separated from each other by astronomically small distances, perhaps 10 million stars per cubic parsec, 1 parsec being 3.23 light years. This core of stars forms a sphere-like structure at the centre of the galaxy called the galactic bulge. This means that the galaxy in profile resembles two fried eggs stuck back to back. Right at the very centre of most galaxies is a supermassive black hole, which may possess millions or even billions of times the mass of our Sun. There is a direct linear relationship between the mass of the galactic bulge and the mass of the supermassive black hole, but what this relationship signifies is as yet unclear. Most star formation in galaxies occurs in the dusty spiral arms. When we look up into the night sky from a dark location free from light pollution, we see one of those spiral arms of our galaxy arcing overhead as a ghostly cloud, a river of light made up of countless stars. This we call the Milky Way. Now this can be confusing, as our entire galaxy is also called the Milky Way. When we see the Milky Way in the sky, we are looking inwards towards the middle of the galaxy. The actual centre of our galaxy lies in the constellation of Sagittarius. Another of Hubble's classifications is barred spiral galaxies. Barred spirals, as their name suggests, are a type of spiral galaxy where a bar of stars extends either side of the galactic core. The spiral arms emanate from each end of the bar, as you can see in this illustration. 2/3 of all spiral galaxies are barred spirals. Surprisingly, our own Milky Way galaxy is a barred spiral, although this was not discovered until 2005 from observations made with the Spitzer Space Telescope. The bars in barred spiral galaxies form when the orbits of stars in the galaxy's inner disk become unstable and deviate from a circular path. This can happen for a number of reasons, including interactions with other galaxies. When two galaxies merge or even just pass close to each other, the gravitational forces can disrupt the orbits of stars in both galaxies. This can lead to the formation of a bar in one or both galaxies. Disk instability. The disk of a spiral galaxy is constantly rotating. This rotation creates a centrifugal force that pushes stars outward. However, the gravity of the galaxy's central bulge pulls stars inward. If the centrifugal force is not strong enough to balance the gravitational pull, the disk can become unstable and form a bar. Gas accretion. Spiral galaxies are constantly accreting gas from their surroundings. This gas can fall into the galaxy's disk and spiral inward towards the centre. As the gas falls in, it can lose energy and cause the stars in the disk to slow down, and this can lead to the formation of a bar. Once a bar forms in a spiral galaxy, it can grow over time by attracting more and more stars into its orbit. The bar can also drive the formation of new stars in the galaxy's centre. This is because the bar can channel gas and dust towards the centre, where it can collapse and form new stars. Bars play an important role in the evolution of spiral galaxies. They can help to distribute gas and dust throughout the galaxy, and they can also drive the formation of new stars. Bars may also be responsible for the formation of active galactic nuclei, or AGNs, which are regions of intense star formation and black hole activity at the centres of some galaxies. The main features of an elliptical galaxy are an elliptical shape. Elliptical galaxies have a smooth ellipsoidal shape. They can range from being almost perfectly spherical to elongated ovals. Little gas and dust. Elliptical galaxies contain very little gas and dust. This is because most of the gas and dust in these galaxies has already been consumed to form stars. Old stars. Elliptical galaxies are primarily populated by old stars. These stars are typically red and low mass. Random orbits. The stars in elliptical galaxies have random orbits. This means that they do not move in a disk or spiral pattern, as is the case in spiral galaxies. Large size. Elliptical galaxies are typically very large galaxies. Some of the largest galaxies in the universe are elliptical galaxies. Preferential location in galaxy clusters. Elliptical galaxies are more likely to be found in galaxy clusters than in the field. High luminosity. Elliptical galaxies are also typically very luminous galaxies. This means that they emit a lot of light. Central supermassive black holes. Elliptical galaxies are thought to contain a supermassive black hole at their centers. The mass of the black hole is correlated with the mass of the galaxy. It is believed that elliptical galaxies form as the result of collisions between two or more galaxies. In the distant future, perhaps in about 4 billion years, our own galaxy and the Andromeda galaxy will collide, merge and form an elliptical galaxy, their graceful spiral forms completely disappearing over millions of years, consumed and torn apart by gravity's relentless maw. This is why elliptical galaxies contain very old stars. They are remnants from the galaxies which collided. Elliptical galaxies, with their paucity of gas, are incapable of giving birth to new stars. This is elliptical galaxy M87 in the constellation of Virgo, some 53 million light-years away. Emanating from its centre is a jet of plasma extending for 5,000 light-years. This jet originates from a supermassive black hole at the centre of the galaxy. In 2017, the Event Horizon Telescope managed to image the black hole in an incredible feat of technology and ingenuity. The radio image of the M87 black hole was on front pages around the world and has since become iconic and will no doubt be written into the history books as our first definitive proof that black holes exist, all evidence of such having hitherto been circumstantial. Well, apart from the main Hubble classifications of galaxies, there are other types. Dwarf galaxies usually comprise just a few million stars and are tiny in comparison to other types, hence their name. They are often found orbiting spiral galaxies, such as the 50 or so found around the Milky Way. Ring galaxies are very rare and comprise a ring of stars surrounding a bright central core. It's not known at present how they form. Irregular galaxies are amorphous galaxies having little or no structure. It's possible they may be the results of galactic collisions. Lenticular galaxies are lens-shaped, hence their name. They are midway between a spiral and an elliptical galaxy. There is much we do not know about how galaxies form and evolve. It is one of the most intense areas of astronomical study. The James Webb Space Telescope, looking back to the dawn of the universe, has shown us early galaxies just a few 100 million years after the Big Bang. How galaxies evolve so quickly in such an astronomically short period of time is not well understood, but it is to be hoped that further JWST observations will shed some light on the conundrum. This image shows some of the very early galaxies imaged by the JWST. It is incredible that we are able to look back in time to the infant universe before the formation of the majestic spiral galaxies. Well, we hope you've enjoyed this introduction to galaxies. Just to summarise, galaxies are vast cities of stars. They're categorised using a system developed by Edwin Hubble. They fall into three main categories: spirals, barred spirals and ellipticals. Galaxies can form clusters comprising up to hundreds of galaxies, and all but a few galaxies have supermassive black holes at their centres. Don't forget to check out our other Astronomy Basics videos in the playlist of the same name on the Space Oddities YouTube channel. Until next time, goodbye.
Yes. Here we are, very close to solar maximum, and it appears that solar maximum is going to occur a little earlier than we thought, perhaps by the end of the year, perhaps the first quarter of next year. And of course, this is a time where there's a lot of solar activity, a lot of coronal mass ejections and flares, sunspots galore, and if you're living in the right places, aurora, not to mention the threat to astronauts, but we won't go there just yet. So we thought it would be good to talk about the sun a little bit, and it turns out that you can understand an awful lot about the sun if you just understand sunspots. Okay, so we're going to talk about the sun today, and this may be a little bit long. We may have to cut this and turn it into a two-parter, but let's give it a go. Let's see where we end up here. Okay, so here's the sun that you might expect to see if you have a a small backyard telescope with an appropriate solar filter. That's our disclaimer, with an appropriate solar filter. And the sun will look different colors depending on the filter. Daz already kind of walked us through how nobody really knows what color the sun is. There are different correct answers. But one of the things that you can see in this image is that the edges of the sun are dark, right? And this is actually real. This is called limb darkening. And it has to do with the fact that the sun is gaseous. And so you can see through parts of it at different depths. And some SOME light gets through at the upper regions and less light as you move down. So this is actually a real image. And if you look on the bottom, you can see a tiny sunspot there. Okay. And this is we've only understood this for about 400 years when Galileo saw sunspots on the sun and he said, there are spots on the sun, and the church said, no way, there are no spots on the sun is pure and pristine. And Galileo proved them wrong, which probably wasn't a good thing to do, but
dangerous thing to do.
The rest is history, as they say.
Yeah.
Here's a little bit better image of the sun. Again, this is in what we call white light. In other words, all the colors of the spectrum that our eyes can see kind of mixed together to produce a white image. And so now we can really see some sunspots. And you'll notice that they have structure. They have different densities. There's a dark inner portion and a lighter outer portion to these sunspots. You might even notice that they tend to occur in pairs. Well, this is all very important information because it helps us understand sunspots. And we're gonna figure out why all this is true in just a few minutes. I think this was supposed to be a video, actually. So I'm not sure what to do with this. I think I'll just move on because it doesn't do what I want it to do.
The sun never does.
It does, yes. They're like comets or cats.
Or Perseid.
So, here we see 6 images of the sun, right? And these are 6 perfectly good images that all look completely different. And most of the reason for this is that the sun and all other objects in the universe look very different depending on the wavelength of light that we use to view them in. In the upper left, we have X-rays. The sun in X-ray, this is taken, of course, above the atmosphere because X-rays are absorbed by our atmosphere, which is a really good thing. And so we're seeing very hot regions of the sun. We're seeing into the corona of the sun that can reach 1.5 million degrees centigrade. Further just to its right in the blue there, by the way, these are colors we made up because we can't see these colors. We see the sun in ultraviolet light, again, from above the atmosphere because very, very tiny amounts of UV radiation make it to the surface of the Earth. So here we're seeing a little bit lower down into the atmosphere, a little cooler. We see a white light image, or V for visual image, on the far upper right. A hydrogen alpha image down below. This is just a very specific form, very restricted format of red light that deals with a transition of electrons in the hydrogen atom. And then infrared and radio. And so the point here is that objects in space look different depending on the wavelength of light that you're using to view them in. In fact, objects on the Earth look different. Well, here's an image of the sun, right? If you're an amateur astronomer, perhaps even if you're not, this is an image of the sun with the moon right in front of the sun, causing a total solar eclipse. So you see the moon is very dark here, and on the outside you see the very soft, tenuous solar corona that you can't see normally because the sun, the photosphere of the sun is just too bright. But look carefully. You can see some structure in the corona. And that structure is reflective, is evidence of the sun's global magnetic field. The particles in the solar corona, many of them are charged particles, and so they are attracted to magnetic field lines. And that's what you see here. The corona is glowing, being attracted to the field lines, and so that gives us that allows us to see some of the sun's magnetic field. That's important for our understanding of the sun and sunspots. So hang on to that. So I've given a lot of talks about the sun, and sometimes they just get so esoteric. And so it occurred to me one day that if you just understand 5 things about sunspots, you can basically understand the entire sun and how it works. So 5 things about sunspots. They're dark, as we have seen. They're cool. So I have Joe Cool on the right-hand side there to remind us. They're highly magnetic. They're associated with solar storms, coronal mass ejections, and flares. And the number one thing to understand about sunspots is they come and go in cycles. So you have the bicycle down there for the,
Don't give up your day job.
Can remind us. So we'll just go on for now. Okay. When we look carefully at sunspots, and this bottom image, by the way, is a ground-based image from a solar observatory, maybe National Solar Observatory, we see that it has structure. It has a dark inner portion and a lighter outer portion. The umbra is the inner portion, the penumbra is the outer portion. And outside of that, we see the bubbling, I'll call it the surface of the sun. It's the what we generally call the surface of the sun, the photosphere, as heat is rising, the sun trying to equilibrate with its surroundings, get rid of its heat that's being generated in the core. So sunspots definitely have structure, and we're going to talk about why. Here's another image of a sunspot up close, just like the one we saw before. The inner darker part, the umbra, is cooler than the surrounding area, the penumbra, which is also cooler than the surface of the sun. Surface of the sun, let's see, we have mostly UK people. So do you guys use centigrade, Fahrenheit, Kelvin? What do you use? It's about 6,000 degrees centigrade. And the inner portion of sunspots may be 3,500, 4,000 degrees centigrade, something like that. And we're going to learn why they're cooler. Well, this was supposed to be a video too. Heck with it. Let's move on. Okay. We have very good evidence now from the physics and from observations, especially a field called helioseismology, which is looking at how the sun rings as sound waves propagate through it, that we can look at the sun as being composed, at least from the photosphere down, into 3 parts: the core, the radiative zone, and the convective zone. In the core, where temperatures can reach 15 million degrees centigrade, centigrade Kelvin doesn't matter at that level, we have fusion taking place where 2 protons are fired together at very high speeds because of the high pressure and temperature to bond together, to bypass that repelling force and actually fuse together. This cannot happen in classical mechanics. And all of the physics that we learned in up to the 1800s, this cannot happen. But we know now through quantum physics that this does happen. So that produces the gamma ray photons that begin in the core of the sun. They migrate out into a region called the radiative zone where they are scattered by electrons, free electrons in that zone. And they're scattered so much, just kind of like a drunk man's walk, if you've heard of that, that it takes on average, statistically, about 100,000 years for that single gamma ray photon to get out of that radiative zone of the sun. 100,000 years. As you move out from the center, it gets cooler and cooler and cooler. And so all of a sudden, you can form atoms. You can have electrons kind of hanging on to nuclei. And as things cool, the most effective means of heat transport is convection. And so they form these convective cells that rotate. And those gamma ray photons hitch a ride on those convective cells, reach the surface of the sun, and then it's 8 1/3 minutes to get to the Earth. Okay. We know sunspots are dark. I've told you they're magnetic, but how do we know? One of the ways we know is that we see a quality when we look at the spectra of sunspots. We see a quality called Zeeman line splitting. Zeeman line splitting. And it means that spectral lines in the presence of very powerful magnetic fields will split into three parts. And we see this visually here of a spectrum where a spectral line has split. That is observational evidence that these sunspots are very magnetic. And the reason they're magnetic is that the sun rotates. But it doesn't rotate like a solid sphere. It rotates like a kind of gloppy, gas. And so the equator of the sun rotates once every 27 days or so. And it's rotating faster than the upper and lower latitudes. So the magnetic field of the sun gets dragged around time after time, month after month after month, until it gets really tangled. You might imagine having if you knit, I don't know how many of you knit, but if you have a big piece of yarn and it's all kind of, clumped together, and you throw it in the bottom of your closet, that piece of yarn might have a little piece of yarn sticking up over all the rest of them, just a little piece. And that in the sun would be a sunspot. And since that little loop of magnetic field is looping above the sun, you have one side and the other. You have a north and a south pole, because magnets have north and south poles. There are no magnetic monopoles. So the sun is sunspots are magnetic, and this is really important. Just an image of the sun in ultraviolet light, showing many, many active regions on the sun. You can even see little loops. If you look on the edges of the sun here, you can see little loops of this plasma. And this is the material rising from a sunspot, from one side of a sunspot, and diving back down into the other, because these plasma obey magnetic field lines, just like as we saw before. So why are they cool? They are relatively cool. And the reason is that the magnetic field in the region of these sunspots is pushing down on that gas that's trying to upwell to the surface. Remember the convective zone just under the photosphere? And since they're pushing down on this gas, it can't get out there, so it has to move around the sunspot and emerges on either side of the sunspot. But the sunspot region itself is cool as a result. Now, okay, this is my favorite slide because it has a little equation in it. And it's actually not that hard to understand. It turns out that a small drop in temperature produces a large drop in brightness. So we just said sunspots are cool, relatively cool. In this equation, L is luminosity or brightness, and it equals 4, that's a number, times pi, that's a number, times radius, which is just a number, times sigma, which is a number, times the temperature to the 4th power. So you modify the temperature just a little bit, raise it to the 4th power, and you have a huge change in brightness. And this is why sunspots are so dark, because they're cool. It also turns out that solar storms, and we're seeing a lot of solar storms these days because we're very near solar maximum, solar storms tend to occur around large sunspot regions. Solar flares, which are generally dominated by electromagnetic radiation, and coronal mass ejections, which are dominated by particle radiation, they tend to occur around sunspot regions. So during solar max, we see lots of sunspots, bigger sunspots in general, and more solar storms. No accident. So, what have we learned about sunspots? They're dark. We know why they're dark. They're cool. We know why they're cool. They're magnetic. We've seen evidence of that. They're associated with solar storms, just because I told you. And and they come and go in cycles, but we haven't talked about the cycles yet. let's see if I have it.
That's fantastic.
Where are we in time? I don't know how to break this up quite.
We've got it. Well, we're half an hour into the show.
Okay. I wonder if well, you let me know. You have a hook. Andy has the hook, and he will hook it around my neck and drag me off as I wave to screaming fans.
Right. Well, I mean, it's all interesting stuff, Luke. So we would love to see it. So no problem at all. Yes, indeed. Right. Well, thank you for that.
Perhaps we'll carry on next week with the rest of us.
Yeah, we can carry on next week.
Yeah, because I mean, Lou, you mentioned the corona being up to 1.5 million degrees in heat, hotter than the actual surface of the sun. Well, just recently I was reading a paper that they think they may have solved that problem, why the corona is so much hotter. And it was, I'm not sure whether it was Betty Colombo or Parker Solar Probe, one of the two.
No, it was the
studying
Solar Orbiter.
Oh, okay, then not even the one I was thinking
Europeans always want to take credit. I mean, come on.
For good reason. We just do it better, that's why.
Of course.
Yeah. What they noticed was that you were talking about these magnetic lines on the surface of the sun, which usually join the spots and all that, but there's also other magnetic activity going on, which gives us the plages, which is the light areas. So there's a lot of magnetic activity going on. But what they found is that it's covered in these little magnetic lines, which apparently are vibrating very rapidly. And they think that this vibration of all these small magnetic filaments is possibly the cause. And like I said, it's possibly, with the sun, we don't know positively, is what's actually heating the actual corona to such a high temperature. And if it's correct, then that's one more nail in the coffin of the mysteries of the sun.
If you remember, Daz, I was showing some images of those last week. And they're like...
Oh, of course, yeah, sorry, yeah.
No problem. Yeah. They're like little magnetic waves that are travelling rapidly across the surface of the sun. And they think that's what's, as Daz said, that's what's heating the corona.
Would these be the Elfin waves? That this was the prevailing theory before Parker was launched.
Don't know.
I couldn't tell you offhand. But also, you were talking about the cycle. Of course, we were expecting cycle 25 to reach its maximum on 2025, but because it's the prediction. This is outdoing all the predictions that they've made so far. They expected the solar spot activity to be very low, like the previous cycle 24 was. And they were then, of course, there was also some people that were expanding that. If we go into, what do they call it, a great solar minimum, which could eventually lead to an ice age. Well, that'll sort out our global warming problem.
I have to break in here. We have been laboring under that theory for a long time. The regions of time where there are essentially no sunspots, the Maunder minimum, and all that, and the ice age that occurred in Europe. During the last one, I think the late 1600s. That appears not to be the case any longer. That the more careful review of the data, I was teaching it. But a more careful review of the data suggests that sunspot minima, even prolonged sunspot minima, do not result in mini ice ages as much as we need a mini ice age right now. I don't think that's borne out by the data.
Not going to happen. Not from that anyway. Oh, that's a shame.
Yeah, because the second minimum you were talking about, was that the Dalton minimum?
Oh, yes, there's
yeah, there was a Dalton. Okay, so that's burst that bubble anyway. But of course, we've got an average of these cycles is 11 years, but they can vary to be as short as 8 years and up to 14 years, I think it was. So the 11-year is an average. And of course, if we're going to go to maximum the end of this year, because the solar spots have appeared a lot more than we were expecting and so much quicker, because if you see a graph, you can see there's a little hump, and the 25th of 2025 was the maximum. Then it's supposed to come back down again. The actuals, if you look at what the actual sunspots have gone, it's actually above the line and climbing still at this very moment. So if we do go to a maximum at the end of this year, it would be interesting to see whether that means we're going to get a very long decline to a minima to cover sort of like more towards the 11 years, or we're going to have a very short cycle. It's fascinating to see it actually pan out, how it's actually going. So it just goes to show that we really, although we know a lot about the sun, we don't know enough to predict anything at the moment. So yeah, as you said, it's very, very interesting.
The problem is that there are two ways that we can make predictions outside of Ouija boards. One is to look at the previous behavior of the sun, right? And we had seen that the solar maximum had been declining over the previous cycles. The other, which would be much more accurate, would be to actually understand the solar cycle, why it is the way it is and what drives it. I mean, there's some thinking that gas moves latitudinally and dives down to the tachocline region below the photosphere and all this stuff. And we don't really understand it. But if we understood the physics well, then we would be able to predict with better accuracy. And we just don't yet.
No. I mean, one thing I did forget to mention is we could also have a double peak of maximum. It can start to decline and then pop back up again. So it's fascinating. I find these sunspots and these cycles. And of course, I think it was Ian mentioned it last week when we mentioned the sun, is that at the end of this cycle, the poles will swap. So that's one of the ways we know that the cycles come to an end. And also with your dual sunspots, they've got polarities. They will also swap. And that's how we know we've come to an end of a cycle. But then you've then got supposedly another cycle. And I think really we need to look at not the 11-year cycles, but the 22-year cycles when things have changed, because there has been some predictions that what they call a south lead cycle tends to have have more interaction with us than with solar weather than a north one does. It's just fascinating. I find this so interesting. And if anybody wants to know a little bit about, I mean, Lou's done a wonderful job as regards telling us about the sunspots. If you look at on the YouTube and look at our the presentation, which was does the solar cycles interact with earthquakes and volcanoes on Earth, have a look at that, and that'll give you a brief description of how these cycles work. So,
and can I just say as well that sunspots are not unique to the sun. We have actually observed them on the surface of other stars. So we know that they are a common feature of stars, that they are sort of intrinsic, if you like, to the activity of stars. For example, here's one on the surface of, let me just make that a bit bigger, of Zeta Andromedae. You can see three clear, astronomers call them star spots, of course, not sunspots, because they're not on the sun, they're on other stars. So these are star spots, and this is another big star called Zeta Andromedae. And I think they've imaged them on Betelgeuse, Regulus, and Antares, if I remember right.
Yes.
I mean, as well as sunspots, you've also got to think about coronal holes, which also give us intense space winds. And Kevin here is talking about plages and faculae, there's a lot of things that actually go on the surface of the sun, which all interact and they all do their own thing. I mean, there's been a couple of this week alone, we've had about 3 or 4 storms come our way from flares and coronal mass ejections. So it's really ramped up at the moment. And if you want to look at this, a website which I've just found recently, it's called solarham.net. Now, if you go to that, you'll be able to look at the sun in different wavelengths, as Lou was pointing out. Every wavelength gives you something different to look at.
What's it called,
and it's solarham.net.
Solarham, as in H-A-M.
Yeah, H-A-M, yeah. Okay. And from there, you can actually link up to NOAA, which is the North American space weather community, or just Google NOAA space weather, and there's one on there called panels. And if you go on the panels, it gives you all these graphs, all these diagrams. And if you go to the actual NOAA site, you can actually watch videos of what's happened in the last few hours and things like that. So and it's all free. So yeah, have a look. It's fascinating.
Right.
It's you can spend hours on it. Anyway, I'm waffling now.
So what
sorry.
we'll do now?
Yeah, lovely talk, though. Lovely.
What
talk,
we'll do now? We will move celestial objects a bit closer to home. We'll move from the sun to the moon.
So I hope you can see this. So the first bit is about the gravitational wave background. Now, let's start off by having a look at, if you like, the spectrum of gravitational waves. As you're probably aware by now, we have detected over 100 gravitational wave events since 2015 using the LIGO detectors in the United States and the Virgo detector in Italy. Now, here we have a scale showing you the frequency of the gravitational waves, what type of objects we can detect at those frequencies, and how we can detect them. So the first thing to say is that between the 1 and 100 hertz frequency, this is what we've been observing at the moment, and this has enabled us to detect merging black holes, colliding neutron stars, collisions between neutron stars and black holes. And this is the limitation, if you can call it that, of the LIGO and Virgo detectors. They're observing in those sort of frequencies. So these are really quite high frequency observations. The instruments are tuned to detect gravitational waves at those frequencies. So these are high frequency, short wavelength, if you like, events. But there are other types of gravitational waves in the universe which are much lower frequency with a much longer wavelength. And in particular, we're talking about the merging of supermassive black holes at the hearts of galaxies. And this is right down here at 10 to the minus 8, 10 to the minus, well, between 10 to the minus 7 and 10 to the minus 9 hertz in frequency. These are much longer wavelength events. It's reckoned that some of these wavelengths could be light years long. And to detect these, one way of doing it is to use pulsars to detect these gravitational waves. Now, to do this, you use the thing is called the pulsar timing arrays. And astronomers have used millisecond pulsars for this. Now, what are these? These are pulsars that have got a rotation speed of less than 10 milliseconds. And we know their rotation speed incredibly accurately. They are the universe's most accurate clocks. They in terms of timing, they rival the most accurate atomic clocks that we have. The fastest spinning millisecond pulsar yet discovered rotates at an amazing 716 times per second. And they thought to spin at that speed because they've been accumulating material from a companion star, which has the effect of speeding up their rotation. But the important thing is here, they are incredibly accurate clocks. Now, astronomers have used 68 of these, all at different distances from the Earth, and as the pulsars spin, these lighthouse-like beams of electromagnetic radiation, be they X-rays or radio, flash in the direction of the Earth so that we can see them. Of course, this is greatly slowed down because these are millisecond pulsars. They're rotating once in less than 10 milliseconds. But I didn't manage to find an animation that would show you that rotation speed, funnily enough. So these are 68 pulsars at different distances from the Earth. And we know exactly, to an incredible accuracy, many, many, many decimal places, exactly how long they take to spin once. So what happens is that you have a gravitational wave which passes through the universe, and this has the effect of delaying or advancing the time at which the pulsars, the signals from these pulsars actually arrive. And by working out exactly how long these signals are advanced or delayed, you can learn something about the gravitational wave that has passed through the universe that has actually done that. Now, look at it another way. Here we have a graphic showing the Earth surrounded by these millisecond pulsars. Far off in the universe, as we know, there are galactic collisions between galaxies, where the two black holes, one in each galaxy, or in some cases more than two galaxies collide, in which case it'd be three, they come together and slowly begin to orbit each other at the center of the galactic merger. Now, they probably orbit each other for, many, many, many thousands of years, but they inexorably come closer together. And as they do, because they're accelerating around each other, they radiate gravitational waves, because anything that accelerates in the universe generates these gravitational waves. How do we know that this happens at the center of galactic clusters with these supermassive black holes? Well, we can actually see it. Here you have an X-ray image of the center of a galactic merger 400 million light years away, and you can see clearly here that there are two superheated disks of material showing up in X-rays, and if they weren't that hot, we wouldn't be able to see them in X-rays. And these two disks surround supermassive black holes. Now, to see the gap between those supermassive black holes at a distance of 400 million light years means that, of course, they're very far apart. Otherwise, we wouldn't stand a chance of being able to split those into two separate objects. Those two black holes are separated by 5,000 light years, believe it or not. That's the gap between the two you can see there. If we add the radio data into that graphic, we can see the jets of material that the black holes are firing out across the universe. And they are swept back, if you like, in this combined radio and X-ray image, because the black holes are plowing through the interstellar medium at about 1,200 kilometers a second. And this forces their jets to be swept back as if they were in a wind, if you like. So we know that we can see these black holes which one day will merge. And as they do get closer together, the gravitational waves from them get stronger and stronger. But the point is that they are very long wavelength, low frequency gravitational waves. Now, why would a pulsar either advance or retard the signal from a pulsar? So if you can imagine, you have a photon leaving a pulsar on its way towards the Earth. And because gravitational waves stretch and squeeze space-time, they stretch it in one direction, squeeze it in another, the photon will actually have to pass through a greater or longer distance, because space is either being stretched or squeezed. And this means that it will, if it's being stretched, the photon will take longer to pass through the gravitational wave, because space is literally being stretched. So the photon takes a longer time to arrive at the Earth. So its arrival is delayed compared to when it should be arriving, because we know exactly when it should be arriving, because they are the universe's most accurate clocks. Similarly, if space is being squeezed, they arrive in advance of when they should arrive. Now, what astronomers have found is this, that there is a background noise in the universe of these gravitational waves, because gravitational waves, according to Einstein, and we have to say we think there are quantum reasons why this probably doesn't happen, but according to Einstein, gravitational waves never die out altogether. They just keep traveling forever. They get weaker, but they never die out altogether. So in the history of the universe, all of these mergers, and there've been probably countless mergers between supermassive black holes, all of these gravitational waves come together over time to form this background hum, if you like, of gravitational waves to the universe. And this is what they've now detected with the pulsar timing array. Now, it has to be said, first of all, that merging supermassive black holes is not the only explanation for this background hum in the universe. There are actually some quite exotic explanations that could be true, but obviously there will be more studies needed to determine exactly what the cause of this hum is. But the most likely candidate is these supermassive black holes. The project to do this, the pulsar timing array, has been running for 15 years. So they've had a chance to collect these long wavelength gravitational waves over 15 years, coming from all over the universe. And the whole point about it is, and the great thing about this is, that the pulsar timing array, well, it's not just one group of scientists. There have been similar experiments going on using pulsars, but using different pulsars in India and other places. And there are several groups that have now all come up with exactly the same results, that there is this background gravitational wave hum, if you like, to the universe, which means that the Earth is being bathed in these gravitational waves all the time. And everything on the Earth, including you, of course, including everything on the Earth, as well as the Earth itself, is being stretched and squeezed all the time by these gravitational waves. Now, you won't feel it, of course, because the difference in size of being stretched and squeezed is about 1,000th the diameter of a proton. But it is happening, and we now have the instrumentation to detect it. So over time, all of these gravitational waves coming from all over the sky merge into this background that has now been detected by the pulsar timing array. For the future, this is fantastic, because what they hope to be able to do is to actually pin down where these gravitational waves come from, what types of objects are producing them. But as I said, it's more likely than not to be merging supermassive black holes. The International Pulsar Timing Array, these are the locations of the telescopes. We have, it includes the biggest radio telescope in the world, the FAST telescope in China. We've got the famous Lovell telescope at Jodrell Bank, of course, in the UK. We've got the Chime telescope in Canada. Arecibo, before its unfortunate demise, was taking part. We've got Meerkat in South Africa, which is a precursor telescope to the world's biggest radio telescope, the Square Kilometre Array, which will be complete hopefully before the end of the decade, although it might be a little bit delayed because of COVID. We got the famous Parkes Radio Telescope in Australia, and we've got a couple of others. But, there have been several groups of scientists working on this and asking the same questions, and they've all got exactly the same results. In fact, the different teams coordinated about when this was going to be released last week, so that nobody was scooped. And there's just some of the telescopes involved. Jodrell Bank, of course, at bottom right, the Chime telescope above it, and so on and so forth. So that was the announcement. We finally detected this gravitational wave background in the universe, and the future for gravitational wave astronomy, which is, let's not forget, only 8 years old as a science. It's already detected this, and this science of gravitational wave astronomy, the first time we've been able to observe the universe in anything other than light electromagnetic radiation, has advanced amazingly in 8 years. And the two LIGO detectors, or the three LIGO detectors, I should say, the two LIGOs in America, and the Virgo detector in Europe are now back online, working together. They came online the last week of May, and they have made lots of detections already. I was looking the other day, one day in particular, they made 9 detections of gravitational wave results yet to be analysed. But even if half of them are terrestrial in origin, and something vibrating on the Earth rather than the vibrations coming from space, then the upgrades that they've undergone over the last couple of years will be well worth it. So we're all really excited about the future of this fledgling science of gravitational wave astronomy.